Welcome, friends. I'm so glad you're here. Whether you're drifting towards sleep, unwinding after a long day, or simply looking for a quiet companion, you found the right place. Before we begin, I'd love to know, where in the world are you listening from? Perhaps you're wrapped in a blanket, sitting by a softly lit window, or resting somewhere under an open sky. Wherever you are, I hope you're warm, comfortable, and ready to wander with me into the cold mathematics of cosmic collision, a journey through deep time and distant space where ice and stone dance with gravity in patterns older than memory. If you find peace or curiosity in these gentle stories, please consider liking the video, subscribing to the channel, or sharing it with someone who might need a moment of stillness too. And to those who've already joined along, thank you. Tonight, we explore not the end of worlds, but the patient mechanics of how worlds change, the quiet astronomy of transformation written in orbital equations and gravitational whispers that speak across billions of years, far beyond Neptune's orbit, in the scattered disk where sunlight arrives weak as candlelight through cathedral glass. A comet nucleus drifts in gravitational silence. The region itself is a testament to the solar system's formation, a sparse collection of icy bodies that never quite managed to coalesce into a planet, scattered instead across distances so vast that neighboring objects remain invisible to each other despite being mountains of ice and stone. Here, in this twilight realm of the solar system, temperatures hover near absolute zero, and a single orbit around the Sun can take hundreds of thousands of Earth years to complete. Comet 3, Atlas measures perhaps 20 kilometers across, roughly the size of a small mountain, yet composed almost entirely of water ice mixed with frozen gases and primordial dust that remembers the solar system's birth 4.5 billion years ago. Its surface bears the color of charcoal, darkened by organic compounds that formed in the cold chemistry of interstellar space before the Sun was born. This dark coating absorbs what little starlight reaches these distant realms, creating temperature differences across the comet's surface that drive the gentle processes of sublimation and erosion. For eons longer than complex life has existed on Earth, this wandering iceberg has followed an elliptical dance so vast that human civilization could rise and fall 1,000 times within a single orbital period. The comet's orbit carries it from the scattered disk, where distances are measured in astronomical units and neighbors are separated by millions of kilometers, to regions slightly closer to the Sun, where ice begins its slow transformation from solid to gas without ever becoming liquid, a process that bypasses the familiar phase transitions we know on Earth. The nucleus rotates slowly, like a sleeping giant turning in cosmic dreams, completing one revolution every few Earth days. This rotation creates the comet's day and night cycle, though the concepts lose their terrestrial meaning in a realm where the Sun appears as just another bright star among countless others. As 3I/Atlas turns, different regions of its surface emerge from shadow to face the distant Sun, beginning the ancient dance of heating and cooling that has continued for geological ages. Its surface bears the accumulated scars of countless impacts from smaller debris, tiny craters no larger than dinner plates alongside ridges and valleys that tell stories of collisions measured in grams rather than megatons. These features preserve a record of the solar system's violent youth, when planetary formations scattered debris throughout space and bombardment rates exceeded anything seen in recent geological time. Each crater represents a moment when some fragment of asteroidal material or cometary debris found its way across vast distances to strike this particular wandering mountain, where the faint touch of starlight reaches the comet's face. Volatile compounds begin their ancient ritual of sublimation. Carbon monoxide molecules, locked in crystalline matrices for millions of years, suddenly break free from their icy prisons and drift away into space. Nitrogen escapes in molecular streams so tenuous they would be invisible to human eyes. Traces of methanol, ammonia, and more exotic compounds drift away like the ghost of some primordial chemistry set, creating the faintest atmosphere around this wandering monument to the early solar system. Scientists call this process outgassing. Though the word seems almost violent for something so gentle, more like a planetary exhale released into the perfect vacuum of space, the escaping gases form what astronomers call a coma, an extremely thin atmosphere that can extend for thousands of kilometers around the nucleus, yet contains less material than Earth's atmosphere would in a volume the size of a small room. It's one of space's gentle paradoxes, something vast in scale yet almost impossibly tenuous in density. Each molecule that escapes carries momentum, creating the tiniest thrust imaginable. Yet over millions of years, these microscopic rocket engines can actually alter the comet's orbit by measurable amounts. It's one of astronomy's quiet ironies that something as delicate as evaporating ice can change the trajectory of a 20-kilometer mountain of stone and frozen water. The effect is so small that it wasn't discovered until spacecraft began making precise measurements of cometary orbits. Yet it accumulates over time like compound interest in some cosmic bank account. The comet's composition tells the story of the solar nebula's outer reaches, where temperatures dropped low enough for water to freeze alongside more exotic ices that remain liquid only at temperatures that would instantly kill terrestrial life. Ammonia ice, toxic to breathe but stable in the extreme cold of the outer solar system. Methane that burns blue in Earth's atmosphere but here remains locked in crystalline silence. Carbon dioxide that we exhale as a gas, but which forms solid dry ice in the comet's deep freeze environment. Mixed throughout this cosmic permafrost are grains of dust older than the sun itself, microscopic survivors from previous generations of stars that died and enriched the galaxy with heavy elements billions of years before our solar system condensed from their scattered ashes. These dust grains carry within their crystalline structures the nuclear signatures of stellar nucleosynthesis, the process by which massive stars forge heavy elements in their cores and scatter them across space when they die in supernova explosions. Some of these dust particles contain diamonds, not the clear gemstones valued on Earth, but microscopic industrial diamonds formed in the shockwaves of stellar explosions and preserved in the comet's frozen matrix like insects in amber. Others carry rare isotopes of elements that can only be produced in the most extreme stellar environments. Tiny chemical fossils that tell the story of the galaxy's enrichment over billions of years. Gravitational perturbations from passing stars have nudged 3Y/Atlas closer to the inner solar system over geological time, like a slow-motion game of celestial billiards played across millions of years. Every few million years, another star passes within a light year or two of the Sun, its gravitational field reaching across interstellar distances to gently tug on objects in the outer solar system. Most of these encounters are so subtle they barely register, changing orbital velocities by mere centimeters per second, but given enough time, these tiny adjustments accumulate into major orbital changes. The comet's path curves according to celestial mechanics as predictable as clockwork, following mathematical laws discovered by Kepler 4 centuries ago and refined by Newton into the universal principles of gravitational attraction. Yet within those precise equations lie probability corridors, narrow mathematical channels where even a slight gravitational adjustment could redirect this frozen wanderer toward Earth's orbital path. The calculations involved require supercomputers to track the gravitational influences of every significant body in the solar system. Yet, they can predict orbital positions thousands of years into the future with remarkable precision. The mathematics are elegant in their precision, describing orbital mechanics with equations that occupy just a few lines on a page. Yet, the universe operates on statistical tendencies rather than absolute certainties. Every gravitational interaction, every stellar flyby, every microscopic thrust from sublimating gases adds tiny corrections to the comet's trajectory. These changes are so small they often fall below the threshold of measurement. Yet they accumulate like sediment in a riverbed, gradually building toward outcomes that would have been impossible to predict from initial conditions. Only a small change in velocity would be required to alter three ice/Atlas's destiny, perhaps 3 or 4 meters per second, no faster than a child walking to school or an adult climbing stairs. Such adjustments happen constantly in the outer solar system as gravitational fields from planets, moons, and distant stars overlap and interact in an intricate dance of mutual attraction that has continued for 4.5 billion years. The remarkable thing is not that orbits change, but that they remain stable for so long despite countless opportunities for disruption. Jupiter's massive presence tugs at objects throughout the solar system with patient persistence. Its gravitational field strong enough to affect trajectories across billions of kilometers. Saturn contributes its own gravitational signature, weaker than Jupiter's, but still significant for objects in the outer solar system. Even the distant ice giants, Uranus and Neptune, exert measurable influences on cometary orbits despite their enormous distances from the scattered disk. The Sun's solar wind carries momentum as well as electromagnetic energy, streaming outward at speeds of hundreds of kilometers per second and creating radiation pressure that can slowly push lightweight objects across vast distances. For 3 ice/Atlas, this pressure is negligible compared to gravitational forces, but for smaller debris and dust particles, solar radiation can dominate orbital evolution over millions of years. Stellar encounters remain rare but inevitable events in galactic time, like lottery drawings held every few million years with odds that eventually favor everyone. Every stellar flyby represents a roll of cosmic dice, with outcomes ranging from negligible orbital adjustments to complete ejection from the solar system. Most encounters send comets tumbling into interstellar space, lost forever to the darkness between stars, where they will drift for billions of years without ever again feeling the warmth of stellar radiation. Others fall inward toward the Sun, where they begin the spectacular process of developing visible comas and tails as increasing solar radiation vaporizes their surface materials. These inbound comets create the celestial displays that ancient civilizations interpreted as omens and portents, bright visitors that appear without warning and fade back into invisibility as they return to the outer darkness. The remarkable truth is not that cosmic impacts occur. They are, in fact, inevitable given enough time and the patient operation of statistical mechanics, but that they remain so improbably rare for any specific object in any given millennium that human civilization has developed in the comfortable illusion of cosmic stability. Earth has been struck by large asteroids and comets throughout its history, each impact leaving signatures in rock layers that geologists can read like chapters in a very long, very slow book written in stone and metal. As 3 ice/Atlas continues its ancient orbit through the scattered disk, ice crystals on its surface catch and reflect starlight with the infinite patience of geological time. Each photon that touches the comet's surface carries a tiny amount of momentum, creating radiation pressure that, over millions of years, can actually change orbital paths by measurable distances. It's another of space's gentle ironies that something as weightless as light can slowly push mountains of ice across the solar system, grain by grain, photon by photon. The comet knows nothing of Earth, nothing of the blue-green world that turns in warmth 4 billion kilometers closer to the Sun, where liquid water flows and life has learned to harness starlight through the quiet alchemy of photosynthesis. 3 ice/Atlas simply follows the gravitational channels carved by mass and distance, drifting through space like a slow-motion raindrop falling through an invisible atmosphere of curved space-time, carrying within its frozen heart the chemical signature of stellar death and cosmic birth, a 20-kilometer time capsule from the solar system's earliest days. Waiting in the cold mathematics of orbital mechanics for the moment when probability and trajectory converge. The mathematics of orbital mechanics unfold in elegant silence across the vast distances of the solar system, where gravitational fields intersect and overlap like invisible rivers flowing through empty space. Each planetary mass creates its own sphere of influence, a region where its gravitational pull dominates over more distant objects. And these spheres shift and interact as the planets themselves move through their ancient orbital dance around the Sun. The gravitational architecture of the solar system resembles a vast three-dimensional web, with dense nodes of influence around massive bodies and tenuous filaments extending across interplanetary space. For Comet 3 Ice/Atlas, drifting in the scattered disk 40 astronomical units from the Sun, the gravitational landscape resembles a complex topographical map where valleys represent stable orbits and ridges mark the boundaries between different dynamical regions. Hills and slopes in this gravitational terrain correspond to zones where small changes in velocity can produce large changes in orbital trajectory. The comet currently occupies what astronomers call a quasi-stable orbit, not permanently bound to any particular trajectory, but moving slowly enough through gravitational space that major changes require millions of years to manifest. The scattered disk itself represents one of the solar system's most dynamically complex regions, where objects drift in loosely bound orbits that can be easily perturbed by distant gravitational influences. Unlike the more predictable orbits of the inner planets, which have been cleared of debris through billions of years of gravitational interactions, the scattered disk remains populated with countless icy bodies in various stages of orbital evolution. Some are bound for ejection into interstellar space. Others will eventually fall toward the inner solar system. Most will simply continue their slow gravitational wandering for millions of years. The mathematics begin with Newton's law of universal gravitation, formulated 3 centuries ago, yet still providing the foundation for all orbital calculations. This deceptively simple equation describes how every mass in the universe attracts every other mass with a force proportional to their masses and inversely proportional to the square of the distance between them. Written in mathematical notation, the law occupies just a few symbols on a page. Yet when applied to the solar system's complex gravitational environment, it generates cascading calculations of extraordinary complexity. When Newton first derived his gravitational law, he solved what astronomers call the two-body problem, the motion of two objects orbiting each other in perfect isolation. The mathematical solution yields elegant elliptical orbits that repeat with clockwork precision, exactly matching the planetary motions that Johannes Kepler had described empirically decades earlier. For two bodies alone in empty space, orbital mechanics becomes a study in mathematical perfection, with every position and velocity calculable to arbitrary precision for any moment in the past or future. Add a third body, and the mathematics transform into something far more complex and fundamentally unpredictable. The three-body problem, as mathematicians call it, has occupied some of history's greatest minds for centuries without yielding a general analytical solution. Henri Poincaré, working on the problem in the late 19th century, discovered that even 3 gravitating bodies can produce chaotic motion, trajectories so sensitive to initial conditions that tiny uncertainties grow exponentially until long-term prediction becomes impossible. This mathematical chaos doesn't mean the motion becomes random or unpredictable in the short term. Newton's laws still govern every instant of the comet's motion with perfect deterministic accuracy. The chaos emerges from the accumulation of tiny influences over vast periods of time, like a pinball bouncing through a machine where each collision amplifies small uncertainties until the final outcome depends on unmeasurable details of the initial conditions. For 3 Ice/Atlas, influenced simultaneously by the Sun's dominant gravitational field, Jupiter's massive presence, Saturn's more distant but still significant pull, and the cumulative effects of countless smaller bodies throughout the solar system, the orbital evolution becomes a study in controlled chaos. The comet's current trajectory appears stable and predictable. Yet embedded within that apparent stability lie seeds of future dramatic change that could manifest across geological timescales. Computer simulations represent the only practical method for tracking such complex gravitational interactions across millions of years. These numerical integrations divide time into small increments, typically a few days or weeks, and calculate the gravitational forces acting on the comet at each moment. Using those forces, the computer predicts the comet's position and velocity at the next time step, then repeats the calculation millions of times to build a detailed map of possible futures. Modern supercomputers can perform these calculations with extraordinary precision, tracking the comet's motion for millions of years while accounting for the gravitational influences of every significant body in the solar system. The simulations include not only the major planets, but also the largest asteroids, the gravitational effects of planetary moons, and even subtle influences like solar radiation pressure and the relativistic corrections to Newtonian gravity predicted by Einstein's general relativity. These computational models reveal the probability corridors that could redirect 3Y/Atlas toward Earth's orbital path. The calculations show that the comet's current trajectory will carry it through the scattered disk for approximately the next million years, gradually precessing through a complex three-dimensional pattern as various gravitational influences tug at its orbit. During this period, the comet will experience hundreds of minor gravitational perturbations and perhaps a dozen more significant encounters with the outer planets. The most dramatic orbital changes typically occur during what astronomers call close encounters, moments when the comet passes within a few astronomical units of Jupiter or Saturn, close enough for the giant planet's gravitational fields to significantly alter the comet's trajectory. These encounters happen roughly once every 100,000 years, creating windows of opportunity for major orbital changes that could redirect the comet toward the inner solar system. The specific mechanism involves what physicists call gravitational scattering, a process analogous to elastic collisions between billiard balls, but operating through the invisible medium of curved space-time. When 3I/Atlas approaches Jupiter, the planet's enormous gravitational field accelerates the comet along its orbital path, adding energy to the orbit and potentially redirecting it toward regions closer to the Sun. The exact outcome depends on a complex interplay of factors: the approach angle, the relative velocities, the precise timing of the encounter, and even the positions of other planets at the moment of closest approach. Jupiter's role as the solar system's gravitational heavyweight cannot be overstated, with a mass more than twice that of all other planets combined. Jupiter dominates the gravitational environment beyond the asteroid belt. The planet acts as both protector and destroyer, sometimes deflecting potentially dangerous comets away from Earth's orbital region, but occasionally redirecting them inward where they become long-period comets that can threaten the inner solar system for thousands of years. The gravitational mathematics reveal a curious asymmetry in these planetary encounters. Most scattering events send comets away from the Sun rather than toward it, flinging them into higher orbits or ejecting them from the solar system entirely. The reason lies in the relative motion of planets and comets. Objects approaching from the outer solar system typically overtake the planets from behind, receiving a gravitational boost that accelerates them beyond solar escape velocity. Only when the orbital geometry aligns in specific ways do planetary encounters redirect comets toward the inner solar system. These favorable configurations require the comet to approach the planet from certain angles and with particular relative velocities, creating a narrow window of orbital parameters that can produce Earth-crossing trajectories. It's one of celestial mechanics' statistical quirks that gravitational interactions favor ejection over capture, making the solar system a gradually emptying reservoir of small bodies. The probability calculations emerging from millions of computer simulations reveal sobering numbers wrapped in statistical uncertainty. For any given millennium, the chance of 3I/Atlas striking Earth remains vanishingly small, perhaps 1 in 10 billion, a probability so low it approaches the mathematical definition of impossibility. Yet time operates differently on astronomical scales, where millions of millennia pass like seasons in a planetary year, and even the most improbable events become statistical certainties given sufficient opportunity. Current orbital models, refined through decades of observations and increasingly sophisticated computer simulations, suggest that 3I/Atlas will remain in the scattered disk for at least another million years before any significant gravitational perturbation occurs. The comet's orbital period stretches across hundreds of thousands of Earth years, meaning it completes fewer than 10 full orbits per million years of solar system evolution. This leisurely pace gives gravitational perturbations time to accumulate gradually, like interest compounding in slow motion across geological timescales. The uncertainty in these long-term predictions grows exponentially with time, a fundamental limitation of chaotic systems that mathematicians call a sensitive dependence on initial conditions. Small uncertainties in the comet's current position and velocity, measurements that lie beyond the precision of present-day telescopes and radar observations, multiply over millions of orbital periods until they encompass vast regions of orbital space. After 10 million years, the mathematical uncertainty becomes so large that the comet could be almost anywhere in the outer solar system, following any of thousands of possible trajectories. Yet within this expanding cloud of uncertainty lie statistical patterns that remain predictable even when specific outcomes become impossible to determine. While astronomers cannot predict whether 3I/Atlas will strike Earth on any particular date millions of years in the future, they can calculate the cumulative probability of impact over geological time scales using well-established principles of orbital dynamics and statistical mechanics. These calculations draw upon decades of observations of the current comet and asteroid populations, combined with geological evidence of past impacts preserved in Earth's rock record. The probability of Earth impact may be incalculable for any specific moment in the distant future, but the cumulative probability over millions of years follows mathematical distributions that astronomers understand with considerable confidence. The resulting impact rate estimates suggest that Earth experiences major comet impacts roughly once every few million years on average, with significant variation around this mean value. Some geological epochs witness multiple impacts within relatively short periods, creating what paleontologists call impact clusters that can dramatically alter the course of biological evolution. Other eras experience impact droughts lasting tens of millions of years, allowing life to diversify and complexify without cosmic interruption. This temporal pattern follows what statisticians call a Poisson distribution, the same mathematical framework that describes radioactive decay, earthquake occurrence, and other seemingly random processes in nature. The distribution reflects the fundamental randomness underlying gravitational encounters in the outer solar system, where the precise timing of orbital alignments cannot be predicted, but the long-term statistical behavior follows well-understood mathematical principles. As 3I/Atlas continues its patient orbit through the scattered disk, the gravitational forces that will ultimately determine its fate operate with the inexorable consistency of physical law. Every moment, the comet's position shifts by a few kilometers relative to its distant orbital focus. Every year, it completes another small fraction of its vast elliptical path around the Sun. Every millennium brings it imperceptibly closer to or farther from the gravitational encounters that could reshape its destiny. While the mathematics of orbital mechanics continue their silent calculation of probability and consequence across the patient expanses of astronomical time, the comet itself remains unaware of these mathematical abstractions, Following the curved paths through space-time that mass and energy carve according to Einstein's equations, it responds only to the immediate gravitational gradient it experiences at each moment, accelerating toward the center of mass of the solar system while simultaneously being tugged sideways by the complex gravitational environment created by planetary motions and the distributed mass of the scattered disk itself. When gravitational mathematics finally converge into reality, when probability corridors collapse into singular trajectory, the first contact between Comet 3, Atlas, and Earth's atmosphere occurs at an altitude of approximately 100 kilometers above the surface, at this boundary between space and sky, where the last wisps of atmospheric molecules drift in near-vacuum conditions. The comet's nucleus encounters resistance for the first time in its 4 billion-year journey through the void. The collision velocity exceeds anything in terrestrial experience, perhaps 30 kilometers per second, fast enough to cross a continent in the time required to draw a single breath. At such speeds, the distinction between solid matter and energy begins to blur according to the physics of extreme conditions. The comet's leading edge compresses atmospheric gases to densities approaching those found in stellar cores, creating temperatures that exceed the surface of the Sun within microseconds of first contact. This initial compression wave propagates ahead of the nucleus itself, a bow shock that announces the comet's arrival through the violent reorganization of atmospheric chemistry. Nitrogen and oxygen molecules, normally content to drift in loose thermal motion, suddenly find themselves crushed together with such force that their molecular bonds shatter and reform in exotic configurations. The familiar blue sky transforms into a plasma sheath, glowing with the characteristic emissions of ionized gases heated beyond the threshold of molecular stability. The physics of hypersonic atmospheric entry operate in regimes where classical mechanics give way to more exotic phenomena. As the comet plunges deeper into Earth's atmosphere, the increasing density creates a feedback loop of compression and heating that builds exponentially with each kilometer of descent. The nucleus itself begins to ablate, shedding layers of ice and rock that instantly vaporize in the superheated plasma wake. What began as a 20-kilometer mountain of pristine ice becomes a fireball, expanding faster than the speed of sound in the surrounding medium. The entry corridor stretches across hundreds of kilometers of upper atmosphere, creating a luminous trail visible from space stations and satellites that briefly witness this intersection of cosmic and terrestrial physics. The plasma tube glows with intensities that overwhelm photographic sensors, radiating energy across the entire electromagnetic spectrum from radio waves to gamma rays. For observers on the ground beneath this celestial blowtorch, the sky itself appears to catch fire as atmospheric molecules dissociate and recombine in cascading chemical reactions. Atmospheric physicists have studied these extreme entry phenomena through computer simulations and laboratory experiments. But nature provides conditions that no terrestrial facility can fully replicate. The combination of velocity, mass, and atmospheric density creates pressure waves that propagate through the entire atmospheric column, reaching the surface as acoustic signatures that precede the visual spectacle by minutes. These pressure pulses, traveling at the speed of sound through atmospheric layers of varying density, create complex interference patterns that focus and amplify the acoustic energy in unpredictable ways. The comet's trajectory carries it through atmospheric layers that have evolved over billions of years to support terrestrial life. The stratosphere, with its protective ozone layer that normally filters harmful ultraviolet radiation, becomes a furnace where ozone molecules decompose instantaneously under the intense energy flux. The troposphere, where weather systems normally distribute heat and moisture around the planet, transforms into a shock tube where pressure waves accelerate to supersonic velocities. As the nucleus penetrates deeper into the atmosphere, the increasing density creates drag forces that begin to decelerate the cosmic projectile for the first time since its journey began. But the deceleration comes at enormous cost in energy dissipation. Every joule of kinetic energy lost to atmospheric drag converts to heat, light, and shock waves that radiate outward at the speed of light. The energy release rate climbs exponentially as atmospheric density increases, reaching levels comparable to the most powerful thermonuclear weapons within seconds of entry. The ablation process strips away the comet's outer layers in a controlled explosion that extends the fireball to dimensions larger than most terrestrial cities. Fragments of the original nucleus, heated to incandescence but still retaining substantial mass, begin to separate from the main body as atmospheric drag overcomes the weak gravitational forces that hold the loosely consolidated comet together. These fragments create secondary fireballs, each following slightly different trajectories as they plunge toward the surface. Spectroscopic analysis of the plasma emissions would reveal the comet's pristine chemical composition to any observers equipped with appropriate instruments. The characteristic spectral lines of water vapor, carbon monoxide, and trace organic compounds that have remained frozen since the solar system's formation now shine with stellar brightness as they undergo their first chemical transformations in 4 billion years. It's one of atmospheric physics' ironies that destruction provides the clearest window into cosmic composition. The physics of atmospheric heating operate on timescales measured in seconds. Yet the energy release affects atmospheric chemistry for months afterward. The intense ultraviolet and X-ray emissions from the plasma fireball create nitrogen oxides and other reactive compounds that will persist in the stratosphere long after the initial event. These chemical byproducts absorb solar radiation differently than normal atmospheric constituents, creating temperature anomalies that propagate through global weather patterns. For the comet nucleus, atmospheric entry represents the violent end of a journey that began in the cold silence of the scattered disk. The pristine ice that preserved the chemical signature of the early solar system for billions of years undergoes complete phase transition in mere seconds, transforming from crystalline solid directly to superheated plasma without ever experiencing the familiar liquid phase. The molecular bonds that held water molecules in stable configuration since before Earth formed finally surrender to the extreme conditions of hypersonic atmospheric entry. The entry fireball reaches maximum brightness at an altitude of approximately 50 kilometers, where atmospheric density provides optimal conditions for energy transfer from the comet's kinetic energy to electromagnetic radiation. At this point, the fireball outshines the sun for observers within hundreds of kilometers of the ground track, creating artificial daylight that overwhelms human vision and saturates photographic instruments. The intense radiation flux heats the Earth's surface below to temperatures sufficient to ignite vegetation and melt exposed metal surfaces. Yet even as the comet nucleus disintegrates in the furnace of atmospheric compression, the largest fragments continue their inexorable descent toward the surface. These surviving pieces, each still containing megatons of kinetic energy, represent the portion of the original mass that will complete the final phase of cosmic collision. Their surfaces glow white-hot from atmospheric heating, but their cores remain cold with the absolute temperatures of deep space, creating thermal gradients that generate internal stresses sufficient to fracture solid rock. The atmospheric physics of large impactor entry remain incompletely understood despite decades of theoretical work and computer modeling. The extreme conditions, temperatures exceeding 10,000 degrees, pressures greater than those found in the deepest ocean trenches, velocities that approach significant fractions of orbital velocity, push matter into regimes where familiar equations of state break down and exotic phases of matter become relevant to the calculation. As the surviving fragments of 3 Ice/Atlas descend through the final kilometers of atmosphere, their passage creates shock waves that focus and amplify through atmospheric reflection and refraction. These acoustic phenomena, traveling ahead of the visible fireball, announce the cosmic visitor's arrival to seismic instruments around the world. The planet itself begins to ring like a struck bell, responding to the atmospheric pressure waves with vibrations that propagate through the solid Earth at the speed of earthquake waves. The final moments of atmospheric transit compress geological timescales into human perception. In less time than required for a hummingbird's wing beat, the largest surviving fragment of the comet nucleus completes its journey from the scattered disk to Earth's surface, carrying within its superheated mass the momentum equivalent of a small mountain accelerated to cosmic velocity. The atmosphere, which has protected Earth from cosmic debris for billions of years, finally yields to an impact energy that exceeds its capacity to absorb and dissipate safely. The moment of impact occurs with the finality of geological time compressed into an instant, when the largest surviving fragment of Comet 3Y/Atlas strikes the Earth's surface. It carries kinetic energy equivalent to millions of nuclear weapons concentrated into a space no larger than a city block. The collision takes place faster than nerve impulses can travel, faster than sound can propagate through solid rock, creating conditions where the normal laws of material science give way to the more exotic physics of extreme states of matter. The impact site, perhaps located on a continental landmass where granite bedrock lies beneath layers of sedimentary stone, becomes the focal point for an energy release that momentarily rivals the power output of the Sun. In the first microseconds of contact, both the comet fragment and the target rock undergo complete transformation from solid matter into superheated plasma. The temperatures reach levels found in stellar cores, hot enough to strip electrons from atomic nuclei and create conditions where matter exists as a soup of charged particles rather than familiar molecular structures. The physics of large impact events operate in regimes that terrestrial experience cannot provide analogies for describing. The pressures generated at the point of contact exceed anything found naturally on Earth's surface by factors of millions, approaching the conditions that exist deep within planetary cores. Under such extreme compression, familiar rocks like granite and limestone behave more like fluids than solids, flowing and deforming according to hydrodynamic principles rather than the mechanical properties that engineers rely upon for earthly construction projects. The initial contact creates what impact physicists call a shock wave, a pressure front that propagates outward from the impact point at velocities approaching the speed of sound in the target material. This shock wave carries energy sufficient to vaporize solid rock, creating an expanding sphere of superheated gas where continental crust once lay. The wave front moves through the surrounding bedrock like a three-dimensional explosion, fracturing and displacing material according to the inverse square law that governs energy distribution in spherical geometry. Within milliseconds of impact, the shock wave carves out a temporary cavity in the Earth's crust whose dimensions dwarf any geological feature created by terrestrial processes. The cavity expands according to fluid dynamics rather than solid mechanics, with the walls flowing outward like liquid despite consisting of rock that normally requires diamond-tipped drilling equipment to penetrate. The expansion continues until the kinetic energy of the impact dissipates through the work of displacing increasingly large volumes of crustal material. The excavation process follows principles that impact cratering specialists have derived from laboratory experiments, nuclear test data, and observations of impact craters throughout the solar system. The initial downward motion of the impactor creates a compression wave that propagates into the target, while the simultaneous sideways expansion of vaporized material drives the formation of the transient crater cavity. The process resembles a controlled explosion buried within the Earth's crust, except that the energy release occurs essentially instantaneously rather than over the seconds or minutes typical of chemical explosives. As the transient cavity reaches its maximum dimensions, gravitational forces begin the process of structural collapse that will determine the crater's final configuration. The cavity walls, temporarily supported by the outward pressure of vaporized rock, lose their structural integrity as the shockwave energy dissipates through the surrounding bedrock. What follows resembles a geological avalanche occurring at velocities measured in kilometers per second, as millions of tons of fractured rock cascade into the void created by the impact. The collapse process operates according to gravitational dynamics modified by the extreme conditions created during cavity formation. The rock that falls into the crater has been fractured and heated by shockwave passage, transforming solid bedrock into a rubble pile of fragments ranging from house-sized boulders to microscopic dust particles. This material accumulates in the crater bottom as impact melt and breccia, new rock types created by the instantaneous melting and recrystallization of pre-existing geological formations. The final crater dimensions reflect a complex interplay between impact energy, target rock properties, and gravitational forces that govern the collapse process. For an impact of 3 I/Atlas's estimated energy, the resulting crater would measure dozens of kilometers in diameter, creating a geographical feature comparable to natural formations like the Chesapeake Bay or the Sudbury Basin in Ontario. The crater rim would rise above the surrounding landscape like an artificial mountain range, composed of rock that has been uplifted and overturned by the impact process. The crater formation timeline compresses geological processes that normally require millions of years into a span measurable in minutes. Mountain building, which typically occurs through tectonic forces operating over geological time, happens essentially instantaneously as the impact lifts crustal material kilometers above its original elevation. Metamorphism, the process by which rocks transform under heat and pressure, occurs in seconds rather than the millions of years required for tectonic metamorphism. New mineral phases, some of which exist nowhere else on Earth, crystallize from the impact melt as temperatures drop from stellar values to merely volcanic levels. The impact creates geological features that preserve a permanent record of the collision in Earth's crustal structure. Shatter cones, distinctive geological formations that form only under shockwave conditions, radiate outward from the impact point in patterns that geologists can recognize millions of years after the event. Shocked quartz grains display microscopic deformation features that require pressures achievable only through meteorite impact or nuclear explosion. These geological signatures provide forensic evidence of ancient impacts long after the craters themselves have been eroded beyond recognition. The excavation process distributes target rock across continental distances according to ballistic trajectories determined by the angle and velocity of ejection from the growing crater. The largest fragments follow parabolic paths that carry them hundreds of kilometers from the impact site before they return to Earth as secondary projectiles. Smaller particles achieve velocities sufficient to reach the upper atmosphere, where they begin the process of global distribution that will eventually deposit impact debris across the entire planet. The energy partition during crater formation follows physical principles that impact specialists have quantified through decades of experimental work. Approximately half the impact energy goes into shockwave propagation through the target rock, heating and fracturing material in a spherical zone around the impact point. Another significant fraction drives the excavation process that carves out the crater cavity and launches debris on ballistic trajectories. The remainder converts to seismic energy that propagates through the solid Earth as earthquake waves carrying the impact signature to seismic stations around the world. The crater itself becomes a window into the Earth's crustal structure, exposing rock formations that normally lie kilometers below the surface. The impact excavation penetrates through sedimentary layers deposited over millions of years, revealing the geological history written in stone beneath the impact site. Basement rocks that formed billions of years ago during the earliest epochs of Earth's history suddenly find themselves exposed to surface conditions, creating opportunities for scientific investigation that would otherwise require deep drilling projects. The thermal effects of crater formation create a localized environment where temperatures rival those found in volcanic systems. The impact melt pools that collect in the crater bottom remain molten for thousands of years, slowly cooling and crystallizing into new igneous rocks that preserve the chemical signature of both the impactor and target materials. These melt rocks provide some of the most direct evidence of impact events, containing chemical and isotopic signatures that distinguish them from ordinary volcanic rocks. The structural geology of the final crater reflects the complex interplay of forces that operated during the formation process. Radial fracture systems extend outward from the crater rim like spokes on a wheel, providing pathways for groundwater flow and creating geological weaknesses that will influence erosion patterns for millions of years. Concentric fault systems record the stages of crater collapse, preserving in stone the sequence of gravitational adjustments that followed the initial excavation for the planet itself. The crater represents both a wound and a geological laboratory where extreme conditions have created new materials and structures. The impact has instantaneously altered the local topography, hydrology, and geological structure in ways that will influence regional development for geological ages. What began as a routine patch of continental crust has been transformed into a complex geological system that will continue evolving through erosion, sedimentation, and tectonic processes long after the immediate effects of impact have faded into the geological record. The crater formation process operates with such violence and speed that it temporarily overwhelms the gradual processes that normally shape the Earth's surface. In minutes, the impact accomplishes geological work that rivers require millions of years to complete, carving valleys and building mountains with an efficiency that demonstrates the awesome power contained within cosmic velocities and planetary masses. The seismic energy released during crater formation propagates through the solid Earth as a complex pattern of earthquake waves that carry the impact signature across continents and ocean basins. These waves travel at velocities determined by the elastic properties of rock deep beneath the surface, racing through the planet's interior faster than any surface phenomenon while bearing the mechanical signature of cosmic collision to seismic stations thousands of kilometers from the impact site. The initial shock wave generated by the impact creates what seismologists call body waves, compression waves, and shear waves that penetrate deep into the Earth's interior before emerging at distant points on the surface. The compression waves, traveling at speeds of 6 to 8 kilometers per second through crustal rocks, arrive first at global seismic networks, announcing the impact event through characteristic signatures that distinguish cosmic collisions from ordinary tectonic earthquakes. These waves carry information about both the impact energy and the geological structure they traverse during their passage through the planet. Behind the initial body waves comes a more complex pattern of surface waves that travel along the Earth's outer shell like ripples spreading across a disturbed pond. These waves move more slowly than the body waves, but carry larger amplitudes and longer durations, creating the sustained ground motion that produces the most dramatic effects at locations far from the impact site. The surface waves wrap around the entire planet multiple times, creating a global resonance that continues for hours after the initial impact as the Earth slowly dissipates the enormous energy input through mechanical vibration. The amplitude and characteristics of these seismic waves depend on the size and velocity of the impactor, the geological properties of the target site, and the distance from the impact to each recording station. For an impact of 3 I/Atlas's magnitude, seismic stations around the world would register ground motions exceeding those produced by the largest natural earthquakes in recorded history. The seismic magnitude would approach or exceed 10 on the Richter scale, a level of energy release that occurs perhaps once every few million years through tectonic processes alone. The wave propagation follows principles of seismic ray theory, with different wave types taking different paths through the Earth's interior according to the velocity structure of mantle and core materials. Some waves travel directly through the mantle as great circle paths connecting impact site to recording station. Others reflect off the boundary between mantle and core, arriving at distant stations after following more complex trajectories through the planet's deep interior. Still others convert between compression and shear motion at interfaces between layers of different composition, creating a rich spectrum of seismic phases that reveal the internal structure of the planet. The Global Seismic Network, designed primarily to monitor nuclear weapons testing and natural earthquake activity, would suddenly find itself recording an event unlike anything in its operational history. The characteristic signatures of impact-generated seismic waves differ from those produced by tectonic earthquakes in ways that seismologists have learned to recognize through studies of nuclear explosions and smaller meteorite impacts. The waves carry higher frequencies, shorter durations, and different radiation patterns that reflect the instantaneous energy release of impact cratering rather than the gradual fault rupture of tectonic activity. Regional effects of the seismic waves begin to manifest within minutes of the impact as the fastest traveling waves reach populated areas hundreds of kilometers from the crater. The ground motion amplitudes in these regions exceed the design criteria for most buildings and infrastructure, creating widespread structural damage even at distances where the direct effects of impact ejecta remain negligible. The shaking continues for minutes rather than the seconds typical of tectonic earthquakes, as multiple wave arrivals from different propagation paths create complex interference patterns. The seismic triggering effect represents one of the most significant secondary consequences of large impact events. The intense ground shaking can activate fault systems that have accumulated tectonic stress over thousands of years, triggering earthquakes along active fault zones across entire continents. These triggered earthquakes follow the primary impact by minutes to hours, creating a cascade of seismic activity that extends the geographical reach of impact effects far beyond the zones directly affected by ejecta or thermal radiation. Volcanic systems respond to the seismic perturbation according to their state of readiness and the characteristics of their magma chambers. Volcanoes that contain pressurized magma bodies near the threshold of eruption may respond to the seismic waves by initiating explosive activity as the ground motion disrupts the delicate equilibrium that normally contains molten rock beneath the surface. The timing of such responses varies from immediate triggering during wave passage to delayed eruptions that occur hours or days after the initial seismic disturbance. The Earth's rotation itself responds measurably to the impact through conservation of angular momentum principles. The sudden redistribution of mass during crater formation and the global propagation of seismic energy create tiny but detectable changes in the planet's rotational velocity and axis orientation. These changes, measured by precision timing systems and satellite geodesy, provide another signature of impact events that persists long after the immediate seismic effects have dissipated through internal friction and wave dispersion. Oceanic regions experience seismic effects differently than continental areas due to the different wave propagation characteristics of water-covered versus solid rock surfaces. The seismic waves traveling beneath ocean basins generate seafloor motion that couples into the overlying water column, creating acoustic waves that propagate through the oceans at the speed of sound in seawater. These acoustic signals can be detected by underwater hydrophone arrays used for monitoring nuclear weapons testing and submarine activity, providing another global detection network for large impact events. The interaction between seismic waves and existing geological structures reveals information about both the impact and the Earth's internal architecture. Waves traveling through sedimentary basins experience different propagation characteristics than those passing through crystalline basement rocks, creating site-specific amplification effects that depend on local geological conditions. These effects explain why seismic damage from large impacts shows complex geographical patterns that reflect underlying geology rather than simple distance-dependent attenuation. Underground facilities experience the seismic effects with particular intensity due to their direct coupling to bedrock motion. Deep mines, subway systems, and buried infrastructure feel the full amplitude of body wave propagation without the buffering effects that soil layers provide for surface structures. The sustained duration of seismic motion from impact events creates special challenges for underground facilities designed primarily to withstand the shorter duration shaking of tectonic earthquakes. The seismic monitoring networks that detect these global waves have evolved from military applications during the Cold War era. When distinguishing underground nuclear explosions from natural earthquakes required precise analysis of seismic wave characteristics, the same analytical techniques that revealed the signatures of nuclear weapons testing now provide the tools for recognizing impact events in the seismic record, creating an unexpected scientific legacy from weapons monitoring technology. Long-period seismic waves, with frequencies below the range of human hearing, carry information about the impact across global distances with minimal attenuation. These waves, traveling through the solid Earth like slow-motion sound waves, maintain their amplitude and characteristics across continental distances, providing a global communication system that announces major geological events to seismic stations around the world. The waves continue circling the planet for hours after the impact, creating a planetary reverberation that gradually fades as energy dissipates through internal friction in rock materials. The cumulative effect of global seismic activity triggered by a large impact creates what geophysicists call a seismic storm, a period of elevated earthquake activity that can persist for weeks as triggered events cascade through fault systems and the Earth's crust slowly readjusts to the energy input. This phenomenon represents one mechanism by which cosmic impacts influence terrestrial geology beyond the immediate vicinity of the crater, demonstrating the interconnected nature of Earth systems and the global reach of cosmic collision effects. As the seismic waves gradually dissipate their energy through propagation and scattering, they leave behind a planet slightly changed by the cosmic encounter. The Earth's internal structure has been probed by seismic energy carrying unprecedented amplitudes and frequencies, revealing details of deep structure that normal tectonic earthquakes cannot illuminate. The global seismic stations have recorded a unique dataset that will provide insights into both impact physics and planetary structure, preserving in digital form the mechanical signature of cosmic collision for future analysis by generations of scientists who may never witness such an event directly. The ejector curtain rises from the expanding crater like a geological fountain, launching fragments of pulverized rock and molten debris on ballistic trajectories that will distribute impact material across continental distances. This curtain of destruction expands outward from the crater rim at velocities approaching several kilometers per second, carrying with it the physical remains of both the impactor and target rocks that have been transformed by shockwave passage into new materials never before seen on Earth's surface. The physics of ejector formation follow principles of ballistic mechanics scaled up to geological proportions. Each fragment launches from the crater according to its position during the excavation process, with material from deeper in the crater achieving higher velocities and longer flight times. The largest blocks, some weighing thousands of tons, follow parabolic trajectories that carry them hundreds of kilometers from the impact site before they crash back to Earth as secondary projectiles capable of creating their own smaller craters. The ejector distribution creates concentric zones of destruction extending outward from the primary crater, each zone characterized by different fragment sizes and impact velocities. The proximal ejector zone, within a few crater diameters of the rim, receives the largest fragments moving at the highest velocities. These house-sized boulders of shocked rock arrive within minutes of the initial impact, creating a moonscape of secondary craters and rubble fields where normal topography once existed. Beyond the proximal zone lies the continuous ejecta blanket, a region where impact debris forms a complete covering over the pre-existing landscape. This blanket consists of rock fragments ranging from gravel-sized pieces to car-sized blocks, all heated to incandescence by their passage through the atmosphere during ballistic flight. The blanket thickness decreases with distance from the crater according to power law, relationships that impact specialists have derived from studies of lunar and planetary crater systems. The ballistic range of ejecta fragments depends on their size, shape, and launch velocity, with smaller particles achieving greater distances due to their higher surface area to mass ratios. The finest dust particles, launched at velocities exceeding several kilometers per second, follow trajectories that carry them beyond the atmosphere entirely. These particles achieve temporary orbital velocities before falling back to Earth over a period of hours to days, creating a global rain of impact debris that settles across the entire planet. The atmospheric passage of returning ejecta creates secondary heating effects that compound the direct thermal radiation from the impact fireball. Each fragment, heated to incandescence during its ballistic flight through the atmosphere, glows like a meteor during its return journey. For observers at distances of hundreds of kilometers from the impact site, the sky fills with thousands of artificial meteors, creating a display more spectacular than any natural meteor shower in recorded history. The collective heating effect of this ejecta rain raises global atmospheric temperatures through radiative heating mechanisms. The fragments, glowing at temperatures of several thousand degrees, radiate thermal energy across the electromagnetic spectrum, with peak emission in the infrared portion that heats the Earth's surface like a planetary oven. The total energy flux from returning ejecta can exceed normal solar heating by factors of 10 or more, creating surface temperatures sufficient to ignite vegetation and melt exposed ice across continental areas. The ignition of global wildfires begins within hours of the ejecta rain as superheated fragments ignite dry vegetation in forests, grasslands, and agricultural regions thousands of kilometers from the impact site. These fires spread according to local wind patterns and fuel availability, but their simultaneous ignition across vast geographical areas overwhelms normal fire suppression mechanisms. The fires create their own weather patterns through convective heating, generating firestorms with winds exceeding hurricane velocities. The smoke and particulate matter released by continental-scale wildfires adds another component to the atmospheric loading created by the impact itself. The combustion products include not only the familiar carbon dioxide and water vapor of normal fires, but also exotic compounds created by the incomplete combustion of vegetation exposed to extreme thermal radiation. These compounds interact with atmospheric chemistry in ways that normal fire emissions do not, creating photochemical reactions that alter atmospheric composition for months after the initial event. The ejecta blanket preserves a record of the impact process in the form of shocked minerals and glass spherules that form only under the extreme conditions of cosmic collision. These materials, scattered across continental distances, provide forensic evidence of impact events that remains detectable in the geological record for millions of years. The spherules, formed by the rapid cooling of molten droplets during ballistic flight, contain chemical signatures that reveal both the composition of the impactor and the target rocks. The secondary cratering process continues for hours after the primary impact as the largest ejecta fragments complete their ballistic trajectories and strike the Earth's surface with velocities measured in kilometers per second. Each secondary impact creates its own small crater and shockwave, adding to the cumulative destruction in regions already devastated by thermal radiation and seismic effects. The secondary craters form chains and clusters that radiate outward from the primary crater, creating distinctive geological patterns that remain recognizable millions of years after formation. The atmospheric disturbance created by the passage of thousands of large ejecta fragments generates acoustic effects that propagate as infrasonic waves through the global atmosphere. These low-frequency sound waves, below the threshold of human hearing, travel around the planet multiple times at the speed of sound in air, creating atmospheric resonances that can be detected by specialized monitoring equipment thousands of kilometers from the impact site. The electromagnetic effects of ejecta formation include the generation of electrical fields and magnetic disturbances as charged particles separate during the high-velocity collision process. The impact plasma creates temporary electrical conductivity in normally insulating rock materials, generating electromagnetic pulses that propagate through the Earth's crust and atmosphere. These pulses can disrupt electronic systems and telecommunications networks across continental distances, creating technological failures that compound the physical destruction from thermal and mechanical effects. The chemical composition of the ejecta reveals the mixing of impactor and target materials that occurs during the shockwave compression and melting process. Isotopic analysis of impact glasses shows the presence of extraterrestrial elements that arrived with the comet, mixed intimately with terrestrial rocks at the molecular level. This chemical signature provides some of the strongest evidence for impact events, since no other geological process can achieve the extreme conditions necessary for such thorough mixing of cosmic and terrestrial materials. The long-term preservation of ejecta deposits depends on local geological conditions and erosion rates, but some impact ejecta layers remain detectable in sedimentary sequences for hundreds of millions of years. These layers serve as time markers in the geological record, providing precise dating horizons that help geologists correlate rock formations across different continents. The most famous example remains the iridium-rich clay layer that marks the Cretaceous-Paleogene boundary 66 million years ago, preserving evidence of the impact that ended the age of dinosaurs. The ejecta curtain itself represents one of nature's most spectacular displays of kinetic energy conversion, transforming the ordered motion of a cosmic projectile into the chaotic trajectories of millions of rock fragments. Each piece of ejecta carries within its crystalline structure the record of pressures and temperatures that briefly exceeded anything achievable through terrestrial processes, creating natural laboratories for studying matter under extreme conditions. As the last fragments of the ejecta curtain complete their ballistic flights and crash back to Earth, they leave behind a planet transformed by the redistribution of crustal material across continental distances. The impact has accomplished in hours what normal geological processes require millions of years to achieve, demonstrating the efficiency with which cosmic collisions can reshape planetary surfaces and alter the course of geological evolution. The atmosphere itself becomes a furnace in the hours following impact, as suspended debris particles absorb solar radiation and re-radiate thermal energy back toward the Earth's surface with an efficiency that transforms the entire atmospheric column into a planetary greenhouse operating at lethal temperatures. The fine dust and vapor clouds launched into the stratosphere by the impact create an absorbing layer that captures incoming sunlight and converts it directly to heat, raising atmospheric temperatures to levels that exceed the tolerance limits of most terrestrial life forms. This atmospheric heating mechanism operates through principles of radiative transfer that atmospheric physicists have studied in laboratory settings and computer simulations, but never before observed operating on planetary scales. The dust particles, ranging in size from microscopic droplets to sand grain-sized fragments, possess optical properties that make them extraordinarily efficient at absorbing electromagnetic radiation across the visible and infrared portions of the spectrum. Each particle acts like a tiny heater suspended in the atmosphere, converting sunlight to thermal energy with an efficiency approaching theoretical maximums. The thermal infrared radiation emitted by these heated particles propagates downward toward the Earth's surface according to blackbody radiation laws, creating an additional heat source that supplements normal solar heating. The combined radiation flux from billions of suspended particles can exceed the normal solar input by factors of 5 to 10, raising surface temperatures to levels normally found only in volcanic environments or industrial furnaces. The heating effect persists as long as the particles remain suspended in the atmosphere, potentially for weeks or months depending on atmospheric circulation patterns. The atmospheric temperature profile undergoes dramatic alteration as the suspended debris creates temperature inversions that disrupt normal convective processes. The stratosphere, normally cooler than the underlying troposphere, becomes superheated by direct absorption of solar radiation by impact particles. This temperature inversion suppresses vertical air circulation, trapping heated air near the surface and preventing the normal cooling mechanisms that would otherwise moderate surface temperatures through convective heat transfer. The infrared pulse generated by atmospheric heating creates surface conditions lethal to most forms of terrestrial life within hours of the impact event. Surface temperatures rise to levels sufficient to denature proteins and disrupt cellular metabolism in plants and animals across continental areas. The heating occurs too rapidly for biological systems to activate protective mechanisms like heat shock proteins or behavioral responses that might provide some protection against more gradual temperature increases. Vegetation experiences thermal stress that overwhelms photosynthetic mechanisms and causes widespread cellular damage through protein denaturation and membrane disruption. Leaves and other plant tissues heat beyond their thermal tolerance limits, causing immediate wilting and death even in species adapted to high-temperature environments. The rapid heating rate prevents the gradual acclimation that allows some plants to survive extreme temperatures in desert environments. The atmospheric heating effect shows complex geographical patterns that depend on local atmospheric conditions, elevation, and the distribution of impact debris in the atmospheric column. Regions beneath dense dust clouds experience more intense heating than areas where atmospheric clearing has begun, creating a patchwork of thermal conditions that varies on scales of tens to hundreds of kilometers. Mountain ranges and other topographical features influence local heating patterns by affecting atmospheric circulation and dust distribution. Water bodies provide some thermal buffering due to the high heat capacity of liquid water. But even large lakes and ocean surfaces warm beyond the tolerance limits of aquatic organisms. The thermal radiation penetrates several meters into clear water, heating the upper layers of aquatic ecosystems to temperatures that cause immediate mortality in fish and other temperature-sensitive species. Shallow water bodies like ponds and streams heat most rapidly, becoming essentially uninhabitable within hours of peak atmospheric heating. The duration of lethal atmospheric heating depends on the settling time of suspended particles and the atmospheric circulation patterns that govern dust distribution and removal. Fine particles with diameters measured in micrometers remain suspended for weeks, while larger fragments settle to the surface within days. The atmospheric residence time follows Stokes's law for particle settling in viscous media, modified by turbulent mixing and convective transport that can either accelerate or retard particle removal depending on local meteorological conditions. The chemical composition of the suspended particles influences their radiative properties and heating efficiency. Silicate dust from vaporized rock absorbs and emits thermal radiation differently than carbonaceous particles from vaporized organic matter or metallic spherules from melted asteroid material. The mixed composition of impact debris creates complex optical properties that vary with particle size, shape, and chemical makeup, leading to heating effects that differ from those produced by volcanic ash or other natural atmospheric aerosols. The atmospheric heating creates feedback effects that alter global weather patterns and atmospheric circulation. The extreme temperature gradients between heated and unheated regions drive convective systems of unprecedented intensity. generating atmospheric disturbances that can persist long after the initial heating pulse has subsided. These meteorological changes propagate through the global atmospheric system, creating weather anomalies that affect regions far from the impact site. The electromagnetic effects of atmospheric heating include changes in atmospheric electrical conductivity as thermal ionization creates charged particles in the heated air masses. These electrical effects can disrupt radio communications and create electromagnetic disturbances that interfere with electronic systems and navigation equipment. The heated atmosphere also generates infrared emissions that can overwhelm thermal imaging systems and create false signatures in satellite-based monitoring systems. Ground-based observations of the atmospheric heating phenomenon would reveal a sky glowing with thermal radiation across the entire infrared spectrum, visible to the naked eye as a diffuse red glow that intensifies during daylight hours when solar heating of the suspended particles reaches peak efficiency. The visible light scattering by dust particles creates optical effects similar to those observed during major volcanic eruptions, but with intensities and durations that exceed anything recorded from natural atmospheric disturbances. The atmospheric chemistry undergoes dramatic changes as the extreme temperatures drive chemical reactions that normally require industrial furnaces or laboratory conditions. Nitrogen and oxygen molecules dissociate and recombine in new configurations, creating nitrogen oxides and other reactive species that alter atmospheric composition. These chemical changes persist long after temperatures return to normal levels, affecting atmospheric chemistry and potentially influencing stratospheric ozone concentrations. The thermal radiation from heated atmospheric particles creates surface heating patterns that depend on atmospheric transparency and local meteorological conditions. Clear skies allow maximum transmission of thermal radiation to the surface, while cloud cover provides some shielding effect that reduces but does not eliminate the heating. The complex interplay between atmospheric absorption, emission, and transmission creates heating patterns that vary on time scales from minutes to hours as atmospheric conditions change. As the atmospheric heating reaches peak intensity in the hours following impact, the Earth's surface experiences temperatures that have not occurred since the planet's earliest history, when a different atmosphere and more active volcanism created similarly extreme thermal conditions. The heating represents a brief return to planetary conditions that existed billions of years ago, demonstrating how cosmic impacts can temporarily reverse billions of years of atmospheric and surface evolution. The gradual subsidence of atmospheric heating as particles settle and atmospheric circulation disperses, the dust cloud marks the beginning of recovery from this phase of impact effects. However, the thermal pulse leaves behind a transformed landscape where vegetation has been destroyed, water bodies have been heated beyond biological tolerance, and surface materials have been altered by exposure to extreme temperatures. The atmospheric heating phase represents just one component of the cascading effects that follow large impact events, but its rapid onset and global reach make it among the most immediately lethal consequences of cosmic collision. In the days following the atmospheric thermal pulse, a different and more insidious transformation begins to affect the global environment as suspended impact debris blocks incoming solar radiation with an efficiency that plunges photosynthetic organisms into an extended winter darker than any natural climate variation in Earth's recent history. The same particles that initially created lethal heating by absorbing and re-radiating solar energy now demonstrate their capacity for blocking sunlight transmission to the surface, creating optical depths that reduce surface illumination to levels insufficient for sustaining plant metabolism. The transition from heating to cooling occurs as larger particles settle from the atmosphere, while the finest dust remains suspended in the stratosphere for months or years. These microscopic particles, with diameters measured in fractions of micrometers, scatter and absorb incoming solar radiation according to principles of atmospheric optics that govern visibility and energy transfer. The particles create what atmospheric scientists call an aerosol loading that rivals or exceeds the effects of the most massive volcanic eruptions in geological history. Photosynthesis, the biological process that converts solar energy into chemical energy and forms the foundation of nearly all terrestrial food webs, requires minimum light levels for efficient operation. The suspended impact debris reduces surface illumination to levels that fall below the compensation point for most plant species, the threshold where photosynthetic energy production exactly balances respiratory energy consumption. Below this threshold, plants begin consuming their stored energy reserves while producing no new organic matter through photosynthetic processes. The wavelength-dependent absorption and scattering properties of impact dust create spectral filtering effects that alter the quality as well as quantity of light reaching the Earth's surface. The particles preferentially absorb certain wavelengths while allowing others to pass through, creating illumination conditions unlike anything in normal terrestrial environments. Plants adapted to full-spectrum sunlight find themselves attempting photosynthesis under artificial lighting conditions that their biochemical machinery cannot utilize efficiently. Forest ecosystems experience particularly severe disruption as the complex vertical structure of tree canopies amplifies the effects of reduced light availability. Understory plants, already adapted to low light conditions beneath the forest canopy, find themselves in essentially complete darkness as the combined effects of atmospheric dust and overhead vegetation eliminate virtually all photosynthetically active radiation. These shade-adapted species, ironically, become some of the first casualties of the lighting catastrophe. Agricultural systems face immediate crisis as crop plants, bred for maximum growth rates under optimal conditions, prove especially vulnerable to light reduction. Modern agricultural varieties, selected for rapid growth and high yields rather than stress tolerance, lack the biochemical flexibility to survive extended periods of severely reduced illumination. Food crops that might normally sustain human populations through temporary disruptions become worthless as they exhaust their energy reserves and die in the artificial twilight. The temporal progression of plant mortality follows predictable patterns based on species-specific energy storage capabilities and metabolic rates. Fast-growing annual plants with minimal energy reserves succumb within days or weeks of light reduction, while longer-lived perennial species with substantial root systems and stored carbohydrates may survive for months before exhausting their reserves. Trees with massive energy storage in woody tissue represent the most resilient components of terrestrial ecosystems, but even these eventually succumb to prolonged darkness. Aquatic photosynthesis faces similar disruptions as reduced light penetration through both atmospheric dust and water columns eliminates primary productivity in lakes, rivers, and ocean surface waters, phytoplankton. The microscopic marine organisms that form the base of oceanic food webs and produce a significant fraction of global oxygen experience massive die-offs as light levels drop below their photosynthetic requirements. The loss of oceanic primary productivity creates cascading effects through marine food webs that mirror the terrestrial ecological collapse. The disruption of photosynthesis creates immediate consequences for atmospheric chemistry as the normal balance between oxygen production and consumption shifts dramatically. Living plants typically produce more oxygen through photosynthesis than they consume through respiration, contributing to the atmospheric oxygen budget that supports animal life. With photosynthesis curtailed while plant respiration continues, ecosystems shift from oxygen sources to oxygen sinks, beginning a gradual reduction in atmospheric oxygen concentrations. The biochemical mechanisms of photosynthetic shutdown involve complex interactions between light availability, temperature, and plant water status. Reduced light levels trigger regulatory responses in plant cells that down-regulate photosynthetic enzyme production and chlorophyll synthesis. These responses, normally adaptive during seasonal changes, become maladaptive when light reduction persists for periods longer than the plant's evolved tolerance ranges. Secondary plant mortality occurs through increased susceptibility to diseases and pest organisms as stressed vegetation loses its natural resistance mechanisms. Plants weakened by energy starvation become vulnerable to fungal infections, insect herbivory, and bacterial pathogens that normally pose minimal threats to healthy vegetation. These secondary effects compound the direct impacts of light reduction, accelerating ecosystem collapse beyond what would result from photosynthetic failure alone. The spatial pattern of vegetation mortality reflects both the heterogeneous distribution of atmospheric dust and the varying light requirements of different plant communities. Desert vegetation, already adapted to harsh environmental conditions, may show greater resilience than mesic forest communities that depend on consistently favorable growing conditions. Ironically, some of Earth's most marginal ecosystems may prove most capable of surviving the artificial climate created by impact debris. Seed banks in soils provide some potential for ecosystem recovery, but their viability depends on the duration of light reduction and the environmental conditions during the dark period. Many seeds can survive extended dormancy periods, but prolonged exposure to altered atmospheric chemistry and temperature fluctuations may reduce germination rates when favorable conditions eventually return. The seed bank represents a biological library of genetic diversity that may or may not survive the cosmic catastrophe intact. The disruption of plant-animal interactions eliminates food sources for herbivorous species across all ecosystem types. Large mammalian herbivores face immediate starvation as their food plants die or become nutritionally inadequate. Smaller herbivores like insects may initially survive by consuming dead plant material, but their populations crash as this resource becomes depleted and no new plant growth occurs to replace consumed vegetation. The time frame for ecosystem collapse depends on the magnitude and duration of light reduction, but computer models suggest that most terrestrial vegetation would be eliminated within 6 months to 2 years of severe light limitation. This time frame reflects the energy storage capabilities of different plant types and the cumulative effects of multiple stress factors operating simultaneously. Even if some individual plants survive the dark period, the disruption of reproductive cycles ensures that many species fail to produce viable offspring, as photosynthetic productivity approaches zero across continental land masses. The Earth's surface begins to resemble planetary environments like Mars or Venus, where atmospheric conditions preclude complex life forms. The temporary return to pre-photosynthetic conditions demonstrates how quickly cosmic impacts can reverse billions of years of biological evolution, stripping away the complex ecosystems that distinguish Earth from other planetary bodies in the solar system. The gradual clearing of atmospheric dust, when it eventually occurs, reveals a transformed landscape where the complex tapestry of terrestrial vegetation has been replaced by barren soils and skeletal remains of forest ecosystems. The photosynthetic shutdown represents perhaps the most profound biological consequence of large impact events. Eliminating the primary productivity that supports virtually all terrestrial life forms and creating conditions for massive extinctions that may persist for thousands or millions of years. The world's oceans begin their own transformation within hours of impact as chemical compounds generated by the collision dissolve into seawater and initiate cascading changes in marine chemistry that propagate throughout the global ocean system. The impact fireball and subsequent atmospheric heating have produced vast quantities of sulfur compounds, nitrogen oxides, and other reactive species that fall back to Earth dissolved in precipitation, creating acid rain of unprecedented intensity and chemical complexity across both terrestrial and marine environments. Sulfur dioxide, liberated from the vaporization of sulfur-bearing minerals in both the comet nucleus and target rocks, undergoes atmospheric oxidation to form sulfuric acid that dissolves readily in water droplets throughout the global atmosphere. When this acidified precipitation reaches the ocean's surface, it begins lowering the pH of seawater from its normal, slightly basic value toward increasingly acidic conditions that challenge the physiological tolerances of marine organisms adapted to stable chemical environments. The acidification process operates through well-understood principles of aquatic chemistry, but the scale and rate of change far exceed anything observed in modern oceanic systems. Normal ocean acidification, caused by absorption of atmospheric carbon dioxide from fossil fuel combustion, proceeds over decades to centuries and involves pH changes measured in tenths of units. Impact-induced acidification occurs over months to years and involves pH shifts of full units or more, creating chemical conditions not experienced in Earth's oceans for hundreds of millions of years. Marine organisms with calcium carbonate shells and skeletons experience immediate stress as acidified seawater begins dissolving their protective structures according to chemical equilibrium reactions that favor dissolution over precipitation. Foraminifera, coccolithophores, mollusks, corals, and countless other species that construct shells and skeletons from calcium carbonate find their life support systems literally dissolving in the increasingly corrosive seawater. The dissolution rate increases exponentially with decreasing pH, creating a chemical environment where shell formation becomes thermodynamically impossible. The disruption of shell formation affects marine food webs at multiple trophic levels, from microscopic plankton that form the base of oceanic food chains to large mollusks and crustaceans that serve as food sources for fish, marine mammals, and seabirds. Pteropods, tiny marine snails that constitute a major food source for fish larvae and adult fish in many oceanic regions, face immediate mortality as their aragonite shells dissolve in acidified water. Their population collapse eliminates a crucial link in marine food webs that support commercial fisheries and marine ecosystems. Coral reef ecosystems experience particularly rapid degradation as the calcium carbonate skeletons that create reef structure begin dissolving faster than living corals can rebuild them. The acidified water attacks both the living coral polyps and the accumulated limestone that forms the reef foundation, creating a feedback loop where structural collapse accelerates chemical dissolution. Entire reef systems, built through thousands of years of biological construction, disintegrate within months as the chemical environment shifts beyond the tolerance range of reef-building organisms. The temporal progression of ocean acidification follows patterns determined by oceanic circulation and the buffering capacity of seawater chemistry. Surface waters experience immediate acidification as they come into direct contact with acid precipitation, while deeper waters remain temporarily protected by the slow mixing rates that characterize oceanic circulation. However, the gradual exchange between surface and deep waters eventually carries acidified water throughout the entire oceanic water column, creating a global chemical transformation. The geographic distribution of acidification effects reflects both the atmospheric distribution of impact-generated acids and the regional variations in oceanic chemistry that influence buffering capacity. Ocean basins with naturally lower alkalinity experience more severe acidification than regions with higher concentrations of dissolved carbonates that can neutralize incoming acids. The Arctic Ocean, with its limited buffering capacity and restricted circulation, may experience particularly severe acidification compared to tropical ocean basins. Marine photosynthesis faces dual stresses from both reduced light availability due to atmospheric dust and altered water chemistry that affects the physiological processes of phytoplankton. Many marine algae rely on calcium carbonate structures for buoyancy control and protection, making them vulnerable to shell dissolution even if they can adapt to reduced light levels. The combined effects of darkness and acidification create conditions where oceanic primary productivity collapses more rapidly than would result from either stress factor alone. Fish populations experience acidification stress through multiple pathways, including direct physiological effects of altered water chemistry and indirect effects from collapse of their food sources. Many fish species rely on carbonate-shelled organisms for food, from larval fish that consume pteropods and foraminifera to adult fish that feed on mollusks and crustaceans. The elimination of these food sources forces dietary shifts that many species cannot accommodate, leading to widespread mortality through starvation and malnutrition. The disruption of marine calcium carbonate production affects global carbon cycling through mechanisms that operate on timescales from months to millennia. Normally, marine organisms remove carbon dioxide from seawater by incorporating it into calcium carbonate shells and skeletons, creating a biological carbon pump that helps regulate atmospheric carbon dioxide concentrations. The shutdown of shell formation eliminates this carbon removal mechanism, potentially contributing to long-term atmospheric carbon dioxide increases that could influence global climate recovery. Deep-sea ecosystems experience acidification effects through the slow but inexorable mixing of surface waters into abyssal depths. Deep-sea organisms, adapted to extremely stable environmental conditions over evolutionary timescales, prove particularly vulnerable to chemical changes as they lack the physiological flexibility to accommodate rapid environmental shifts. The cold, high-pressure conditions of deep ocean environments also favor calcium carbonate dissolution, accelerating the chemical attack on shell-bearing organisms. The chemical buffering systems that normally maintain stable ocean pH become overwhelmed by the massive acid inputs from impact-generated atmospheric chemistry. Seawater contains natural buffers, primarily the carbonate system, that resist pH changes through chemical reactions that consume added acids. However, these buffering systems have finite capacity and become progressively less effective as the total acid loading approaches or exceeds their neutralization capacity. Marine sediments provide some buffering through dissolution of calcium carbonate deposits accumulated over millions of years on the ocean floor. This geological buffering operates slowly, requiring centuries to millennia for full effect, but it eventually helps neutralize excess acidity and begin the process of chemical recovery. The dissolution of seafloor carbonates represents a geological response to impact-induced chemical perturbation, demonstrating how cosmic events can trigger feedbacks that operate across vastly different timescales. The recovery of normal ocean chemistry depends on the rate of acid input, the efficiency of natural buffering systems, and the time required for atmospheric clearing to eliminate the source of acidifying compounds. Computer models suggest that severe acidification could persist for centuries to millennia, depending on the magnitude of the initial impact and the resilience of oceanic chemical systems. The recovery timeline far exceeds the generation times of most marine organisms, ensuring that ecosystem recovery requires evolutionary adaptation rather than simple population regrowth. As oceanic pH continues its downward trajectory in the months following impact, marine ecosystems experience a chemical reset that eliminates millions of years of evolutionary adaptation to stable ocean chemistry. The acidification represents one of the most fundamental alterations of marine environmental conditions since the evolution of complex life, creating selection pressures that will shape the trajectory of marine evolution for millions of years into the future. The chemical transformation of Earth's oceans demonstrates how cosmic impacts influence planetary systems through complex cascading effects that extend far beyond the immediate physical destruction at the impact site. The dissolution of marine shells and skeletons, the collapse of oceanic food webs, and the disruption of global biogeochemical cycles illustrate the systemic nature of impact effects and their capacity to alter the fundamental chemical environment that supports life on Earth. The planet's ice sheets respond to the altered atmospheric conditions with a sensitivity that reflects their role as climate system amplifiers, where small changes in temperature and precipitation patterns trigger massive adjustments in ice mass that influence global sea level and regional climate patterns for thousands of years beyond the immediate impact effects. The reduced solar radiation reaching Earth's surface through the dust-laden atmosphere creates cooling conditions that favor ice accumulation, while the disrupted atmospheric circulation patterns alter the distribution of moisture and heat transport that normally maintains ice sheet equilibrium. The Greenland ice sheet, containing enough frozen water to raise global sea level by 7 meters if completely melted, begins accumulating additional ice mass as surface temperatures drop below the melting threshold across increasingly large areas of its surface. The atmospheric dust reduces solar heating so effectively that even the low elevation margins of the ice sheet, which normally experience summer melting, remain frozen throughout the year. This shift from net melting to net accumulation reverses decades of ice loss and initiates a period of ice sheet growth not seen since the most recent glacial period. Antarctic ice sheets demonstrate even more dramatic responses to the altered climate conditions, as their massive size and elevation make them particularly sensitive to changes in atmospheric temperature and circulation. The West Antarctic ice sheet, normally balanced precariously between accumulation and melting, shifts decisively toward accumulation as atmospheric cooling eliminates the marine ice shelf melting that normally regulates its mass balance. The ice sheet begins expanding both vertically through increased snowfall and horizontally through reduced calving rates at its marine margins. The mechanisms of ice sheet response operate through feedback systems that amplify initial climate changes through albedo effects and atmospheric circulation modifications. Fresh snow covering expanded areas of the planet's surface reflects increasing amounts of solar radiation back to space, reducing surface heating and creating conditions that favor additional ice accumulation. This ice albedo feedback operates as a positive feedback loop, where initial cooling creates conditions that promote further cooling through increased reflection of solar energy. Atmospheric circulation patterns undergo reorganization as the temperature gradients between ice-covered and ice-free regions create new patterns of air mass movement and storm track development. The expanded ice sheets generate high-pressure systems that deflect storm tracks and alter precipitation patterns across continental areas. These circulation changes affect not only regions adjacent to ice sheets, but also distant areas connected through atmospheric teleconnection patterns that can transmit climate signals across ocean basins. The altered precipitation patterns favor snow accumulation over rain across higher latitudes and elevated regions where temperatures remain below freezing for extended periods. Mountain glaciers that have been retreating due to recent warming begin advancing as increased snowfall and reduced melting create positive mass balances for the first time in decades. Alpine regions experience the reformation of glacial systems that had disappeared during previous warm periods, demonstrating the rapid response of mountain ice to changed climate conditions. Sea ice formation proceeds at accelerated rates in polar regions as surface cooling and reduced atmospheric heat transport create conditions favoring ice growth over melting. Arctic sea ice, which normally reaches minimum extent during late summer, maintains year-round coverage as atmospheric dust blocks the solar heating that normally drives seasonal ice retreat. The expanded sea ice coverage creates additional albedo feedback that reinforces atmospheric cooling and promotes further ice formation. The oceanic response to ice sheet growth involves complex interactions between freshwater input from increased ice melting during the transition period and the eventual reduction in freshwater input as ice sheets shift to net accumulation. Initially, the disrupted atmospheric conditions may accelerate ice melting in some regions while promoting accumulation in others, creating complex patterns of sea level change that vary regionally according to the distribution of ice mass changes and the gravitational effects of ice sheet loading. Continental ice sheets that disappeared thousands of years ago begin reforming as atmospheric conditions shift toward those that characterized glacial periods in Earth's recent geological history. The Laurentide ice sheet, which once covered much of northern North America, begins rebuilding as snow accumulation exceeds melting across the Canadian Shield and northern plains. Similarly, Scandinavian ice sheets start reforming as persistent snow cover in northern Europe transitions to permanent ice accumulation. The timescales of ice sheet response span from immediate effects measured in months to long-term adjustments that continue for millennia after atmospheric conditions stabilize. The initial response involves changes in surface melting and snowfall that affect ice sheet mass balance within the first growing season after impact. However, the full dynamic response of ice sheets, involving changes in ice flow patterns and thickness distribution, requires centuries to millennia as the ice responds to altered surface conditions through viscous deformation and gravitational adjustment. The hydrological cycle experiences fundamental reorganization as increased ice storage reduces the amount of water available for circulation through atmospheric and oceanic systems. River systems fed by glacial melt experience dramatic flow reductions as their source glaciers shift from melting to accumulating regimes. This affects not only water supply for human systems, but also the sediment transport and nutrient delivery that maintain downstream ecosystems and coastal environments. Permafrost regions experience complex responses as atmospheric cooling favors permafrost expansion, while altered precipitation patterns affect soil moisture and vegetation that insulate frozen ground. Some permafrost areas may actually thaw initially due to changes in snow cover that affect ground insulation, while others experience deeper freezing as atmospheric cooling overwhelms surface insulation effects. The net result depends on regional variations in temperature change, precipitation patterns, and vegetation responses. The loading effects of expanded ice sheets create isostatic depression of the Earth's crust beneath growing ice masses, triggering slow but measurable vertical land movements that affect relative sea level changes. Areas beneath expanding ice sheets subside under the weight of accumulated ice, while regions adjacent to ice sheets experience uplift as crustal material flows away from loaded areas. These vertical land movements continue for thousands of years after ice loading occurs, creating complex patterns of relative sea level change. Ocean circulation patterns respond to the freshwater inputs from ice sheet changes and the altered density structure created by modified temperature and salinity distributions. Thermohaline circulation, the global ocean conveyor belt driven by density differences, may slow or reorganize as fresh water from ice melting reduces seawater density in critical formation regions. These circulation changes affect heat transport between ocean basins and can amplify or moderate regional climate responses to atmospheric changes. The biological consequences of ice sheet expansion include habitat changes that affect species distributions and ecosystem structure across high-latitude regions. Tundra ecosystems experience compression toward lower latitudes as ice sheets expand, while boreal forest zones shift toward regions that remain ice-free. These habitat changes occur faster than many species can migrate or adapt, creating potential for significant ecological disruption beyond the immediate effects of atmospheric and temperature changes. As ice sheets continue growing in response to the altered atmospheric conditions, they begin exerting increasing influence on global climate through their effects on atmospheric circulation, ocean currents, and solar radiation reflection. The expanded ice coverage transforms Earth's climate system toward conditions resembling those of glacial periods, demonstrating how cosmic impacts can trigger climate transitions that persist far longer than the immediate atmospheric disturbances created by the collision event itself. The ice sheet response represents one of the most long-lasting consequences of large impact events, as ice sheets can continue growing for thousands of years after atmospheric conditions return to normal. Maintained by the feedback systems they create through albedo effects and circulation changes, the cosmic impact thus initiates a climate transition that may persist until orbital cycles or other long-term climate drivers create conditions favorable for ice sheet retreat and the eventual return to pre-impact climate conditions. The collapse of terrestrial ecosystems follows predictable patterns that ecologists have studied through mathematical models and observations of environmental catastrophes. But the scale and simultaneity of impact-induced ecological destruction exceeds anything documented in recorded natural history. Species extinction proceeds in waves that radiate outward from the immediate impact zone, with each successive wave affecting different groups of organisms according to their ecological vulnerabilities and life history characteristics. The first wave of extinctions occurs within hours to days of impact, affecting species most vulnerable to immediate environmental changes such as thermal stress, atmospheric chemistry alterations, and direct physical trauma from ejecta bombardment. Large-bodied animals with high metabolic rates and limited behavioral flexibility prove particularly susceptible to rapid environmental changes. Lacking the physiological adaptations or behavioral repertoires necessary to survive sudden shifts in temperature, atmospheric composition, and habitat structure, flying organisms experience immediate mortality as atmospheric conditions become unsurvivable due to toxic gas concentrations, thermal radiation, and particulate matter that clogs respiratory systems. Birds, bats, and flying insects encounter atmospheric chemistry that overwhelms their respiratory physiology. While the mechanical trauma from suspended debris particles creates additional mortality factors, migratory species caught in flight during the impact event face complete population elimination as their aerial environment becomes lethally hostile within hours. Large mammals demonstrate particular vulnerability to the cascading environmental changes through their dependence on extensive habitat areas and complex food webs that collapse under impact stress. Megafauna species with limited population sizes and slow reproductive rates lack the demographic resilience necessary to survive even brief periods of elevated mortality. Their extinction occurs through multiple pathways: direct thermal stress, habitat destruction, food source elimination, and disruption of social structures necessary for reproduction and survival. The second wave of extinctions unfolds over weeks to months as food web collapse eliminates the ecological relationships that support species dependent on specific trophic interactions. Herbivorous species face starvation as plant communities die under reduced light conditions and atmospheric toxicity. The loss of primary productivity creates a demographic bottleneck that propagates upward through food webs, affecting carnivorous species that depend on herbivore populations for sustenance. Specialist species with narrow ecological niches experience extinction rates far exceeding those of generalist species capable of exploiting multiple food sources and habitat types. Obligate relationships between plants and their pollinators, predators and their prey, and parasites and their hosts collapse as environmental changes eliminate one or both partners in these co-evolved relationships. The loss of ecological specialists reduces ecosystem complexity and eliminates millions of years of evolutionary adaptation to specific environmental conditions. Marine ecosystems demonstrate parallel patterns of extinction as oceanic acidification and reduced primary productivity eliminate species adapted to stable chemical and biological conditions. Filter-feeding organisms that depend on planktonic food sources face immediate starvation as oceanic primary productivity collapses. The elimination of these species removes crucial ecosystem services such as water filtration and nutrient cycling that maintain marine ecosystem function. The spatial pattern of ecosystem collapse reflects both distance from the impact site and regional variations in ecosystem resilience and environmental buffering capacity. Ecosystems in geographically isolated locations, such as islands, demonstrate particular vulnerability due to their limited species pools and reduced opportunities for recolonization from external source populations. Continental ecosystems show more complex patterns of survival and extinction based on topographical features that provide environmental refugia and corridors for species movement. Aquatic ecosystems in protected basins or groundwater-fed systems may provide temporary refugia for some species, but their long-term viability depends on connections to larger ecological networks that supply genetic diversity and demographic support. Small, isolated water bodies become ecological islands where species may survive the initial impact effects but face eventual extinction through demographic stochasticity and genetic isolation unless connectivity to other populations can be re-established. The third wave of extinctions occurs over months to years as the secondary effects of ecosystem disruption eliminate species that survived the initial environmental changes but cannot persist in the altered ecological landscape. These delayed extinctions result from factors such as reproductive failure due to disrupted mating systems, increased disease susceptibility in stressed populations, and competitive exclusion as species with different tolerances compete for limited resources in degraded habitats. Soil ecosystems experience profound disruption as the complex communities of bacteria, fungi, protists, and invertebrates that drive nutrient cycling and decomposition face lethal conditions from atmospheric toxicity and altered soil chemistry. The loss of soil biota eliminates the biological processes necessary for plant establishment and growth, creating feedback loops that prevent ecosystem recovery even when atmospheric conditions improve. Soil formation, normally requiring thousands of years, must begin anew in areas where biological soil communities have been eliminated. Plant reproduction faces multiple barriers in the post-impact environment, including lack of pollinators, unsuitable germination conditions, and absence of mycorrhizal fungi necessary for seedling establishment. Even if adult plants survive the initial impact effects, reproductive failure ensures population decline and eventual extinction unless vegetative reproduction can maintain populations until sexual reproduction becomes viable again. The temporal scale of ecosystem collapse varies among different biological communities, with some ecosystems losing most species within months, while others maintain reduced functionality for years before reaching ecological collapse thresholds. Ecosystem resilience depends on factors such as species diversity, functional redundancy, and the availability of environmental refugia that can serve as sources for recolonization when conditions improve. Freshwater ecosystems demonstrate particular vulnerability to impact effects due to their limited volume and direct connection to terrestrial systems that supply both water and nutrients. Lakes and rivers receive concentrated inputs of toxic compounds from atmospheric deposition and terrestrial runoff, creating chemical conditions that exceed the tolerance ranges of freshwater organisms. The small size and isolation of many freshwater systems prevent recolonization from external sources, even if local populations survive the initial impact. Predator-prey relationships become unstable as environmental stress affects different species unequally, creating mismatches between predator survival and prey availability. Top predators experience particularly severe impacts as the collapse of lower trophic levels eliminates their food sources, while their position at the top of food webs exposes them to concentrated toxic compounds through bioaccumulation. The loss of apex predators removes ecological regulation that normally maintains population balance among prey species. The genetic consequences of population bottlenecks during mass extinction events include loss of genetic diversity that reduces evolutionary potential for surviving populations. Small populations that survive the initial extinction waves face increased risk of extinction through genetic factors such as inbreeding depression and loss of adaptive variation. The genetic legacy of impact-induced extinction may influence evolutionary trajectories for millions of years as reduced genetic diversity constrains adaptive responses to future environmental changes. Competition for remaining resources intensifies among surviving species as ecological niches become vacant and resource availability decreases. Species with broader ecological tolerances may expand into niches formerly occupied by extinct specialists, but the overall reduction in ecosystem productivity limits the total number of individuals and species that can be supported. Competitive interactions may accelerate extinction processes for species already stressed by environmental changes. As ecosystem collapse reaches its most severe phase, the remaining biological communities consist primarily of species with broad environmental tolerances, rapid reproductive rates, and flexible behavioral repertoires. These survivor communities represent a dramatically simplified version of pre-impact ecosystems, lacking the complexity and specialization that characterized mature ecological systems. The biological world undergoes a reset towards simpler community structures reminiscent of early successional stages, but operating under environmental conditions that may prevent the development of complex ecosystems for extended periods. The ultimate extent of ecosystem collapse depends on the magnitude of environmental changes and the duration of hostile conditions. But even relatively brief periods of severe environmental stress can eliminate species and ecological relationships that required millions of years to evolve. The cosmic impact demonstrates nature's capacity for both creation and destruction, showing how geological forces can rapidly undo biological complexity that accumulated over vast periods of evolutionary time. Human infrastructure reveals its fundamental vulnerability to cosmic-scale disturbances as the cascading effects of impact reach technological systems designed for terrestrial rather than astronomical threats. The electromagnetic pulse generated by the impact fireball propagates through Earth's atmosphere and magnetosphere with an intensity that overwhelms electronic systems across continental distances, creating failures that cascade through interconnected networks and disable the technological foundation upon which modern civilization depends. The electromagnetic effects begin with the ionization of atmospheric gases in the impact fireball, which creates a temporary conducting medium that interacts with Earth's magnetic field to generate intense electromagnetic radiation across a broad spectrum of frequencies. This pulse travels at the speed of light, arriving at distant locations within milliseconds of the impact and inducing voltages in conducting materials that exceed the design tolerances of electronic components by factors of hundreds or thousands. Electrical power grids experience catastrophic failure as the electromagnetic pulse induces current surges in transmission lines that overwhelm protective systems and damage transformers, generators, and distribution equipment across thousands of square kilometers. The interconnected nature of power grids means that failures cascade rapidly through the network, as protective systems disconnect damaged sections and redistribute loads beyond the capacity of remaining infrastructure. Within hours, electrical power disappears across continental areas encompassing hundreds of millions of people. Communication systems suffer immediate and comprehensive failure as the electromagnetic pulse disrupts radio transmissions, damages satellite electronics, and overwhelms ground-based transmission equipment. Cell phone networks, internet infrastructure, broadcast systems, and emergency communication networks cease functioning simultaneously, eliminating the information systems that coordinate modern society's response to emergencies. The communication blackout prevents coordination of disaster response efforts and leaves populations isolated from information about conditions beyond their immediate vicinity. Transportation infrastructure experiences multi-layered disruption as electronic control systems fail, fuel distribution networks cease operating, and navigation systems become unreliable or completely non-functional. Modern vehicles with electronic engine management systems refuse to start or operate erratically as their computer systems suffer electromagnetic damage. Air traffic control systems fail globally, grounding commercial aviation and eliminating rapid long-distance transportation. Rail systems dependent on electronic signaling and control systems cease operation to prevent collisions in the absence of coordination. Financial systems collapse as the electronic networks that manage modern banking. Trading and monetary transactions suffer complete failure. Credit card processing, electronic fund transfers, stock market operations, and banking systems that exist primarily as electronic records become inaccessible when their supporting computer infrastructure fails. The absence of functional payment systems paralyzes commercial transactions and prevents the economic coordination necessary for disaster response and recovery efforts. Supply chain networks, dependent on electronic coordination and just-in-time delivery systems, experience immediate disruption that propagates through global commerce within days. Manufacturing systems requiring electronic process control cease production. Inventory management systems that track goods movement become non-functional. The complex logistics networks that deliver food, medicine, fuel, and other essential supplies to urban populations break down as electronic coordination systems fail and transportation networks become unreliable. Water treatment and distribution systems face operational challenges as electronic control systems fail and backup power sources prove inadequate for extended operation. Municipal water supplies that depend on electric pumps, electronic monitoring systems, and automated chemical treatment processes begin failing within hours of power loss. Sewage treatment facilities cease operation, creating public health hazards as untreated waste accumulates in urban areas. The failure of water infrastructure creates immediate threats to human survival in densely populated areas. Medical infrastructure experiences comprehensive failure as hospitals lose power, electronic medical equipment ceases functioning, and pharmaceutical supply chains break down. Life support systems, diagnostic equipment, and electronic medical records become inaccessible at the moment when medical services face unprecedented demand from impact-related injuries and environmental health effects. The failure of refrigeration systems threatens vaccine and medicine supplies, while the absence of communication systems prevents coordination of medical response efforts. Food distribution systems collapse as refrigeration fails, transportation networks become unreliable, and electronic inventory management systems cease operation. Grocery stores, restaurants, and food processing facilities lose their ability to maintain fresh food supplies, creating immediate food security challenges for urban populations dependent on daily deliveries of perishable goods. Agricultural systems face disruption as automated feeding, irrigation, and environmental control systems in modern farming operations fail without electronic control systems. Industrial facilities experience widespread shutdown as process control systems fail and safety systems activate to prevent accidents in the absence of normal monitoring and control capabilities. Chemical plants, refineries, nuclear power facilities, and manufacturing operations implement emergency shutdowns to prevent catastrophic failures. But these shutdowns eliminate production of essential materials and energy supplies needed for disaster response and recovery. The failure of heating and cooling systems creates immediate habitability challenges as buildings lose climate control during a period when atmospheric conditions may require protection from extreme temperatures, toxic gases, or particulate matter. Modern buildings designed for mechanical environmental control become uninhabitable without functional HVAC systems, forcing population movements towards structures that can provide passive environmental protection. Emergency response systems suffer comprehensive failure as communication networks, transportation systems, and coordination mechanisms cease functioning simultaneously. Fire departments, police forces, emergency medical services, and disaster management agencies lose their ability to coordinate response efforts or communicate with affected populations. The absence of emergency services during a period of maximum need creates conditions where additional casualties result from the failure of disaster response infrastructure. Military and defense systems experience varying degrees of failure depending on their electromagnetic hardening and independence from civilian infrastructure. Some military communication and command systems may remain functional due to specialized electromagnetic protection, but their effectiveness becomes limited by the failure of supporting infrastructure such as fuel distribution, civilian communications, and transportation networks that military operations depend upon for logistical support. The cascading nature of infrastructure failure creates feedback loops, where the failure of one system accelerates the failure of others through interdependent relationships. Power system failures disable communication systems, which prevents coordination of power restoration efforts. Transportation system failures prevent delivery of replacement parts and fuel needed for infrastructure repair. The interconnected nature of modern infrastructure creates vulnerabilities where cosmic-scale disturbances can trigger systemic failures that persist long after the initial electromagnetic effects have subsided. Rural populations may experience greater resilience to infrastructure failure due to their reduced dependence on electronic systems and greater self-sufficiency in essential resources like food, water, and energy. However, rural communities also face challenges from the failure of communication systems that normally coordinate agricultural production and connect rural areas to urban markets and services. The restoration of functional infrastructure requires not only replacement of damaged electronic components, but also coordination of repair efforts across multiple interdependent systems simultaneously. Without functional communication and transportation systems, the coordination necessary for infrastructure repair becomes extremely difficult, potentially extending the duration of system failures far beyond the time needed for simple component replacement. As electronic systems remain non-functional across continental areas, human societies experience a sudden reversion to pre-electronic technological capabilities, demonstrating the extent to which modern civilization depends on electronic infrastructure for basic survival functions. The cosmic impact reveals the fragility of technological systems designed for terrestrial threats and the cascading vulnerabilities that emerge when astronomical events interact with human technological dependencies. The slow process of atmospheric recovery begins according to the patient laws of fluid dynamics and particle physics. As the suspended debris that has darkened skies and altered global climate gradually settles from the atmosphere under the inexorable pull of gravity. The settling rates follow Stokes's law for particles falling through viscous media, with larger fragments descending rapidly while microscopic dust remains suspended for months or years, creating a stratified clearing process that occurs in predictable temporal and spatial patterns. The largest particles, with diameters measured in millimeters, complete their atmospheric residence within days of the impact as gravitational forces overcome atmospheric drag and turbulent mixing. These particles create the first visible signs of atmospheric clearing as they fall like a gentle rain of cosmic debris, covering the Earth's surface with a thin layer of impact glass, shocked minerals, and condensed rock vapor that tells the chemical story of cosmic collision. Their removal from the atmosphere allows the first increase in surface light levels since the initial impact event. Mid-sized particles with diameters in the range of micrometers remain suspended for weeks to months. Their settling rates, determined by the balance between gravitational acceleration and atmospheric drag in the varying density and circulation patterns of the global atmosphere. These particles contribute most significantly to the optical depth that blocks solar radiation, and their gradual removal drives the slow brightening of surface conditions that enables the eventual resumption of photosynthetic activity in surviving plant communities. The finest dust particles, with diameters measured in fractions of micrometers, demonstrate atmospheric residence times extending to years or even decades as their tiny mass provides insufficient gravitational force to overcome atmospheric turbulence and circulation patterns that can maintain them in suspension indefinitely. These particles, comparable in size to the aerosols produced by major volcanic eruptions, continue affecting global climate long after the coarser debris has settled, maintaining reduced solar transmission and altered atmospheric chemistry. Atmospheric circulation patterns play crucial roles in determining both the global distribution of settling debris and the regional variations in atmospheric clearing rates. The general circulation of the atmosphere, driven by solar heating and Earth's rotation, creates preferred pathways for particle transport that result in heterogeneous deposition patterns across the planet's surface. Some regions experience rapid clearing as atmospheric circulation carries particles away, while others accumulate additional debris transported from distant areas. The jet streams, high-altitude air currents that circle the globe at velocities approaching 100 kilometers per hour, create highways for rapid particle transport that can carry impact debris around the planet multiple times before gravitational settling removes it from the atmosphere. These high-altitude transport pathways explain how impact debris can appear in atmospheric samples collected thousands of kilometers from impact sites, demonstrating the global reach of atmospheric particle distribution. Precipitation plays an important role in accelerating particle removal through washout processes that capture suspended debris in raindrops and snowflakes. The impact particles serve as condensation nuclei for water droplets, creating precipitation that carries debris to the surface more rapidly than would occur through gravitational settling alone. However, this precipitation also concentrates toxic compounds from the impact debris, creating localized areas of contaminated soil and water that pose long-term environmental challenges. The atmospheric chemistry continues evolving as reactive compounds generated by the impact undergo slow chemical transformations in the stratosphere and troposphere. Sulfur compounds oxidize to form sulfuric acid aerosols that contribute to both atmospheric opacity and acid precipitation. Nitrogen oxides participate in complex photochemical reactions that alter atmospheric composition and affect the formation of ozone in both beneficial and harmful ways. Depending on altitude and local atmospheric conditions, temperature gradients in the atmosphere create convective circulation patterns that either accelerate or retard particle settling, depending on whether upward or downward air motion dominates in particular regions. Areas beneath strong convective systems may experience delayed clearing as upward air motion counteracts gravitational settling, while regions with predominantly subsiding air masses clear more rapidly as downward motion enhances particle removal rates. The stratosphere demonstrates different clearing characteristics than the troposphere due to its stable temperature structure and limited vertical mixing. Particles injected into the stratosphere by the impact fireball remain suspended longer than those confined to the troposphere, creating a reservoir of long-lived atmospheric opacity that continues affecting global climate after tropospheric clearing has progressed substantially. The stratospheric clearing occurs primarily through slow transport to the troposphere, followed by more rapid removal through precipitation and turbulent mixing. Seasonal variations in atmospheric circulation patterns affect clearing rates as changes in solar heating and atmospheric temperature gradients alter circulation patterns throughout the year. Winter conditions in high latitudes may favor longer particle residence times due to reduced convective activity, while summer circulation patterns may accelerate clearing through enhanced vertical mixing and precipitation. These seasonal effects create temporal variations in the atmospheric recovery process that depend on the timing of the impact relative to Earth's annual cycle. Regional geography influences atmospheric clearing through topographical effects that alter local circulation patterns and precipitation characteristics. Mountain ranges create orographic lifting that enhances precipitation and accelerates particle removal on windward slopes, while creating rain shadows with delayed clearing on leeward sides. Coastal regions may experience different clearing rates than continental interiors due to the influence of maritime air masses and sea breeze circulation patterns. The optical properties of the atmosphere change gradually as particle concentrations decrease and size distributions shift towards smaller particles that scatter light differently than the mixed particle populations present immediately after impact. The spectral characteristics of transmitted sunlight evolve as selective absorption and scattering by different particle types create wavelength-dependent transmission that affects both the quantity and quality of solar radiation reaching the surface. Biological indicators provide sensitive measures of atmospheric recovery as surviving organisms respond to gradual improvements in light availability and air quality. Lichens, among the most sensitive biological indicators of atmospheric chemistry, begin showing signs of recovery as toxic gas concentrations decrease and particulate matter settles from the air. Plant communities demonstrate gradual improvements in photosynthetic activity as light levels increase and atmospheric chemistry returns toward conditions compatible with biological processes. Satellite observations, if any orbital infrastructure survives the electromagnetic effects of impact, would reveal the global patterns of atmospheric clearing through measurements of atmospheric optical depth and particle distribution. The view from space would show a gradual transition from global atmospheric opacity to regional clearing patterns that reflect the complex interplay of atmospheric circulation. Particle physics and regional geography in determining recovery rates. The atmospheric recovery represents one of the first signs of planetary healing following cosmic impact, as the natural processes that maintain atmospheric composition and clarity gradually overcome the massive perturbation created by the collision. However, the timescale of complete atmospheric recovery, measured in months to years for full clearing, far exceeds the immediate survival needs of most biological communities, ensuring that atmospheric effects contribute significantly to the long-term consequences of impact events. As atmospheric transparency slowly returns and surface illumination increases toward pre-impact levels, the recovering atmosphere reveals a transformed landscape where the biological and physical consequences of cosmic collision have reshaped the planet's surface features and ecological systems. The atmospheric clearing marks not a return to pre-impact conditions, but rather the beginning of a new phase in planetary evolution where surviving systems must adapt to altered environmental conditions and reduced biological diversity. The patient mechanics of atmospheric particle settling demonstrate nature's capacity for self-restoration through physical processes that operate independently of biological recovery, providing one pathway toward planetary healing that continues even in the absence of complex life forms. The clearing atmosphere creates opportunities for biological recovery while revealing the full extent of changes that cosmic collision has wrought upon the Earth's surface and living systems. Life persists with a tenacity that reflects billions of years of evolutionary adaptation to environmental catastrophe, finding refuge in protected environments where cosmic impact effects prove less severe and biological processes can continue despite the wholesale transformation of surface conditions. These refugia, scattered across the planet like biological islands in a sea of devastation, preserve fragments of pre-impact ecosystems and provide the genetic seed stock from which planetary recovery may eventually proceed. Deep cave systems offer some of the most secure refugia, where constant temperatures, protection from atmospheric toxicity, and isolation from surface conditions create stable environments that buffer organisms from the extreme fluctuations occurring at the surface. Cave-adapted species, already specialized for survival in low-energy environments, demonstrate remarkable resilience to the altered atmospheric chemistry and reduced food inputs that characterize post-impact conditions. These ecosystems, sustained by groundwater inputs and the slow decomposition of organic matter, maintain biological activity even as surface ecosystems collapse. Geothermal environments provide another category of refugia, where heat sources independent of solar radiation create local energy oases that can support biological communities despite global cooling and atmospheric opacity. Hot springs, geysers, and geothermal vents harbor thermophilic microorganisms and specialized plant communities that derive energy from chemical processes rather than photosynthesis. These systems demonstrate how life can exploit alternative energy sources when traditional solar-powered ecosystems fail. Deep soil environments, protected by meters of overlying material from direct atmospheric contact, preserve communities of bacteria, fungi, and invertebrates that continue ecological processes such as decomposition and nutrient cycling. The soil biota, operating in a buffered chemical environment where temperature fluctuations remain moderate and toxic compounds become diluted through adsorption and chemical reaction, maintains the biological foundation necessary for eventual surface ecosystem recovery. Groundwater systems provide refugia for aquatic organisms in environments that remain chemically stable and thermally buffered compared to surface water bodies. Deep aquifers, springs, and cave streams maintain biological communities that escape the acidification and thermal effects experienced by surface waters. These groundwater refugia preserve freshwater biodiversity and provide sources for recolonization of surface aquatic systems when environmental conditions improve. Marine deep-sea environments demonstrate remarkable stability compared to surface ocean systems, as their isolation from atmospheric contact and thermal buffering by massive water columns create conditions where impact effects remain minimal. Deep-sea hydrothermal vents, sustained by geological rather than solar energy, continue supporting diverse biological communities based on chemosynthetic primary production. These deep ocean oases maintain marine biodiversity and ecological processes independent of the surface ocean collapse. Seed banks buried in soils provide dormant repositories of genetic diversity that can survive extended periods of hostile surface conditions. Many plant species produce seeds with exceptional longevity, capable of remaining viable for decades or centuries while waiting for favorable germination conditions. These seed banks represent biological time capsules that preserve the genetic information necessary for ecosystem reconstruction, though their ultimate viability depends on soil chemistry and temperature conditions during the extended dormancy period. Microbial communities demonstrate extraordinary resilience to environmental extremes through physiological adaptations that allow survival under conditions lethal to complex organisms. Bacterial and archaeal communities can enter dormant states, alter their metabolism to exploit alternative energy sources, and tolerate chemical and physical conditions that exceed the tolerance ranges of plants and animals. These microbial refugia maintain the fundamental biological processes of decomposition, nutrient cycling, and chemical transformation that form the foundation for ecosystem function. High elevation environments may provide refugia through their naturally harsh conditions, which pre-adapt organisms to environmental stresses similar to those created by impact effects. Alpine and Arctic species, already tolerant of extreme temperatures, limited growing seasons, and variable atmospheric conditions, may demonstrate greater resilience to post-impact environmental changes than species from more benign environments. These high-elevation refugia preserve cold-adapted biodiversity and ecosystem types. Protected valley systems and geological depressions may create microenvironments where topographical features provide shelter from atmospheric effects and create locally moderated conditions. Deep valleys can trap warmer air and provide protection from wind-blown particulates, while their enclosed nature may buffer chemical changes and maintain more stable conditions than exposed terrain. These topographical refugia create opportunities for survival of less specialized organisms in protected locations. Underground root systems and rhizome networks of perennial plants provide another form of biological refugia where living tissues remain protected below ground while surface portions die back under hostile atmospheric conditions. Many plant species can survive extended periods with only their root systems alive, regenerating surface growth when favorable conditions return. These underground plant refugia preserve genetic diversity and provide the foundation for vegetation recovery without requiring seed germination under difficult conditions. Ant and termite colonies, with their complex underground tunnel systems and social organization, create protected environments where insect societies can survive periods of surface environmental hostility. These social insect colonies maintain organized communities capable of exploiting stored food resources and adapting their behavior to changing environmental conditions. The survival of social insects preserves important ecological functions such as soil modification and organic matter processing. Aquatic refugia in deep lakes and isolated water bodies may preserve communities where thermal stratification and chemical buffering create stable conditions despite regional environmental changes. Large, deep lakes maintain stable temperatures and chemistry in their hypoliminion layers, providing refugia for cold-adapted aquatic species. These aquatic refugia preserve freshwater biodiversity and maintain ecosystem functions that can serve as sources for broader recovery. The adaptation process within refugia involves both behavioral and physiological adjustments as surviving organisms modify their activities and metabolic processes to accommodate altered environmental conditions. Reduced food availability selects for energy conservation strategies, while altered atmospheric chemistry favors organisms with tolerance for chemical extremes. These adaptive responses occur through both individual behavioral flexibility and population-level selection for traits that enhance survival under post-impact conditions. The genetic bottlenecks experienced by populations surviving in refugiae create founder effects that will influence the evolutionary trajectory of recovery ecosystems. Small surviving populations carry reduced genetic diversity that constrains adaptive potential while potentially fixing beneficial mutations through genetic drift. The genetic legacy of refugial survival will shape the characteristics of future ecosystems as surviving lineages undergo evolutionary radiation into vacant ecological niches. Communication and migration between refugia become critical factors determining the long-term viability of surviving populations and their potential for ecosystem reconstruction. Isolated refugia may maintain local populations, but lack the genetic exchange necessary for long-term evolutionary viability. While connected, refugia can support larger effective population sizes and maintain gene flow that preserves adaptive potential. As environmental conditions gradually improve with atmospheric clearing and climate stabilization, the refugial populations begin the slow process of expansion and recolonization that will determine the structure and function of recovery ecosystems. The survival and adaptation occurring within refugia represents the biological foundation for planetary recovery. Preserving the genetic and ecological resources necessary for life's eventual return to dominance on a cosmic impact-altered Earth. The refugial communities demonstrate life's remarkable capacity for persistence under extreme conditions, maintaining biological processes and genetic diversity through periods of environmental catastrophe that test the limits of organismal tolerance. These biological sanctuaries provide hope for planetary recovery while illustrating the conservative nature of evolution, which preserves life's essential functions even when surface conditions become temporarily incompatible with complex ecosystems. The geological perspective emerges slowly as the immediate chaos of cosmic collision settles into the patient rhythms of deep time, where the violent transformation of planetary surface features begins its integration into the longer narrative of Earth's structural evolution. The impact crater, carved in minutes from solid rock, begins its own geological journey through the processes of erosion, sedimentation, and tectonic modification that will gradually incorporate this cosmic scar into the planet's continuing crustal development over millions of years. Erosional processes begin immediately as atmospheric precipitation, no longer intercepted by vegetation, flows directly across exposed rock surfaces and newly fractured terrain created by the impact. The absence of protective plant cover accelerates soil formation through mechanical and chemical weathering of shocked rock materials, creating sediment loads in streams and rivers that exceed normal values by factors of hundreds. This accelerated erosion redistributes impact debris across drainage basins, spreading the chemical signature of cosmic collision through sedimentary systems that will preserve the impact record in layered deposits. The crater itself undergoes structural modification as gravitational forces and subsurface fluid flow alter the initial impact morphology through processes that operate on time scales from years to millennia. Impact-fractured rock provides pathways for groundwater circulation that drives chemical weathering and gradual mass wasting of crater walls. Hydrothermal systems, powered by the residual heat of impact melts, circulate mineral-rich fluids that deposit new minerals and alter existing rock compositions, creating unique geological formations found only in impact structures. Sedimentation patterns throughout the region surrounding the impact site reflect the massive inputs of eroded material from the crater and surrounding terrain disrupted by shockwave passage. Lakes and ocean basins receive unprecedented sediment loads that create distinctive stratigraphic sequences marking the impact event in geological time. These impact-related sediment packages will remain recognizable in the rock record for hundreds of millions of years, providing permanent testimony to the cosmic collision embedded in Earth's crustal structure. The impact melt rocks cooling in the crater bottom undergo slow crystallization over thousands of years, forming igneous rock types with unique chemical and textural characteristics that distinguish them from ordinary volcanic rocks. These impact melts preserve the mixed chemistry of both the cosmic impactor and terrestrial target rocks, creating mineralogical assemblages that serve as chemical fossils of the collision event. The cooling and crystallization process creates rock formations with distinctive shock metamorphic features that remain diagnostic of impact origin throughout subsequent geological time. Tectonic responses to the impact develop over longer timescales as the Earth's crust adjusts to the sudden mass redistribution and structural disruption created by crater formation. The removal of crustal material during excavation creates isostatic imbalances that drive slow vertical movements as the crust seeks new equilibrium configurations. Regional fault systems may be reactivated by impact-generated stress fields, creating earthquake activity that continues for thousands of years as crustal adjustments propagate through surrounding rock formations. The biological recovery process begins with the gradual re-establishment of microbial communities in soils and sediments where chemical conditions have stabilized sufficiently to support cellular metabolism. Pioneer microorganisms, emerging from refugial populations or arriving through atmospheric transport, begin the slow process of ecosystem reconstruction by re-establishing fundamental biogeochemical cycles. These microbial communities modify soil chemistry and create conditions more favorable for the eventual establishment of plant communities. Plant colonization of disturbed terrain follows predictable successional patterns, with pioneer species adapted to harsh environmental conditions gradually giving way to more complex plant communities as soil development and local climate modification create increasingly favorable growing conditions. The re-establishment of vegetation occurs first in protected microsites, where local topography provides shelter from extreme atmospheric conditions and accumulated organic matter improves soil fertility. The temporal scale of biological recovery spans orders of magnitude, from initial microbial colonization occurring within years to the development of mature forest ecosystems requiring centuries or millennia. The recovery timeline depends on factors such as the availability of seed sources, soil development rates, climate stability, and the complex interactions between establishing plant and animal communities. Some ecosystem types may never fully recover their pre-impact characteristics due to irreversible changes in soil chemistry, hydrology, or regional climate patterns. Evolutionary processes operating on surviving populations drive adaptive radiation as species exploit vacant ecological niches created by mass extinction. The reduced competition and abundant ecological opportunities in post-impact environments favor rapid evolutionary change as surviving lineages diversify to fill empty ecosystem roles. This evolutionary radiation may produce new species and ecological relationships within thousands to millions of years, demonstrating life's capacity for creative response to environmental catastrophe. The global carbon cycle undergoes long-term modification as the massive release of carbon dioxide from vaporized carbonate rocks and the reduction in biological carbon sequestration alter atmospheric composition for thousands of years. The recovery of atmospheric carbon dioxide to pre-impact levels depends on the rates of biological recovery, carbonate rock weathering, and oceanic carbon absorption, creating complex feedbacks between geological and biological processes that influence global climate evolution. Ocean chemistry recovery follows timescales determined by the rates of acid neutralization through carbonate dissolution and the gradual restoration of biological processes that regulate seawater composition. The deep ocean provides buffering capacity that moderates chemical changes, but complete recovery of normal marine chemistry may require thousands of years as biological communities re-establish and resume their roles in biogeochemical cycling. Climate system recovery involves complex interactions between atmospheric clearing, biological productivity recovery, ice sheet adjustments, and ocean circulation changes that operate on multiple timescales simultaneously. Some climate effects may persist for millennia as ice sheet configurations and ocean circulation patterns established during the impact period continue influencing regional and global climate long after atmospheric conditions have returned to normal. The fossil record created by impact-related extinction and recovery events becomes embedded in sedimentary sequences that provide future geologists with detailed documentation of cosmic collision effects. The sharp discontinuity in fossil assemblages marks the impact horizon, while the gradual changes in subsequent layers record the pace and pattern of biological recovery. These geological archives preserve the history of cosmic catastrophe and biological resilience for scientific investigation millions of years in the future. Mineral formation during impact and recovery creates unique geological materials that serve as indicators of cosmic collision processes. Shocked minerals with distinctive crystallographic features, impact diamonds formed under extreme pressure conditions, and unusual chemical compounds created by impact chemistry provide diagnostic signatures that allow identification of ancient impact events long after their topographic expressions have been erased by erosion. The integration of impact effects into ongoing geological processes demonstrates how cosmic collisions become part of Earth's normal crustal evolution rather than isolated catastrophic events. The impact crater. Initially a violent disruption of geological order, gradually becomes incorporated into regional geological structure through the same processes of erosion, sedimentation, and tectonic modification that shape all crustal features over geological time. As millions of years pass, the cosmic impact becomes just another chapter in Earth's geological history, preserved in rock formations and fossil assemblages, but no longer dominating the planet's surface features or biological communities. The impact joins the geological record alongside volcanic eruptions, mountain building episodes, and climate changes as one more demonstration of the dynamic processes that continuously reshape planetary surfaces and drive the evolution of life. The deep time perspective reveals cosmic impacts as integral components of planetary evolution rather than external disruptions to geological and biological order. These events, catastrophic on human timescales but routine in astronomical time, represent one mechanism by which the solar system continues to influence planetary development billions of years after initial formation, Maintaining the connection between cosmic and terrestrial processes that has operated throughout Earth's history, the cosmic dance continues in its ancient rhythm, as it has for billions of years, as it will for billions more. In the cold mathematics of orbital mechanics, other comets drift through the scattered disk, following their own patient trajectories through the gravitational channels carved by planetary masses and stellar encounters. The impact of 3I/Atlas becomes just one moment in the vast temporal expanse of planetary evolution, a punctuation mark in the longer sentence of cosmic time that connects the formation of the solar system to its eventual dissolution billions of years in the future. Earth turns on its axis, carrying the scars and healing landscapes of cosmic collision through the familiar cycle of day and night. The impact crater, now weathered by countless seasons of rain and snow, fills gradually with sediment and returning life. Lakes form in protected depressions. Streams carve new channels through fractured rock. The patient work of geological time transforms violence into landscape, catastrophe into habitat, cosmic collision into terrestrial geography. Life, in its infinite creativity and resilience, explores the vacant niches and altered environments with the quiet persistence that has characterized biological evolution since the first cells learned to capture sunlight and transform it into the chemical energy of existence. New species emerge from the genetic bottlenecks of survival, their characteristics shaped by the environmental pressures of a transformed world. Evolution continues its patient exploration of possibility, writing new chapters in the 4-billion-year story of terrestrial biology. The atmosphere clears to transparency, revealing skies as blue as they were before cosmic ice and stone rewrote the rules of planetary habitability for a few brief moments in geological time. Clouds form and dissipate according to the eternal patterns of weather and season. Rain falls on growing forests. Snow accumulates on reforming glaciers. The hydrological cycle resumes its ancient circulation, carrying water from ocean to cloud to river to sea in the endless loops that have sustained life for billions of years. In the deep ocean, where thermal vents continue their patient chemistry and darkness maintains the same eternal silence it has known since the planet's formation, life continues the slow elaboration of complexity that requires no external energy beyond the heat of radioactive decay and the gravitational energy of planetary formation. These deep communities, unchanged by cosmic collision, preserve in their biochemistry the memory of Earth's earliest life, maintaining the molecular traditions that connect present biology to the chemical experiments that began in primordial seas. The planet sleeps in its orbital motion, carrying the stories of cosmic collision and biological recovery through space at 30 kilometers per second, following the same elliptical path around the Sun that it has traced for billions of years. Other worlds turn in their own orbits, some bearing life, some sterile, all participating in the gravitational symphony that holds the solar system in its stable configuration across the vast expanses of astronomical time. In the scattered disk, beyond the orbit of Neptune, new comets begin their own slow journeys toward possible encounters with the inner planets, carrying within their frozen nuclei the chemical signatures of stellar death and rebirth that tell the story of galactic evolution across billions of years. The cosmic cycle continues, as inevitable as gravity, as patient as time itself, connecting Earth to the vast universe that gave birth to both stone and star, to ice and life, to the cosmic collisions that punctuate planetary evolution with moments of transformation that echo across geological ages. The silence of space embraces everything: comets and planets, impacts and recoveries, extinctions and radiations, holding all these events in the same eternal quiet that has characterized the universe since the first atoms formed and began their long dance toward complexity. Consciousness. and the cosmic perspectives that allow intelligence to contemplate its own origins in stellar nuclear fusion and planetary accretion across the patient vastness of deep time.